Long before the first dinosaurs walked on land, Earth's oceans were alive with giant, fearsome creatures unlike anything we see today. These ancient waters were ruled by powerful predators with sharp teeth, massive jaws, and strange alien shapes. From the armoured Dunkleosteus to the fast and deadly Anomalocaris, these prehistoric monsters dominated the seas with strength, speed, and mystery. Before we begin this prehistoric journey, let us know where in the world you're watching from, and what time it is for you right now. Drop it in the comments below and settle in for a fascinating ride back in time. Megalodon was a truly colossal shark that once ruled the oceans. Its scientific name is Otodus megalodon, and it belonged to a now extinct group of sharks known as the Otodontidae. For a long time, scientists believed Megalodon was closely related to today's great white shark, but further research showed that it actually came from a different lineage that split off from the great white's ancestors during the early Cretaceous period, over 100 million years ago. Megalodon lived during a vast stretch of time, from around 23 million years ago to about 3.6 million years ago. It first appeared in the early Miocene epoch and vanished during the early Pliocene, long before humans ever walked the Earth. Even though it's one of the most famous prehistoric predators, we've never found a complete skeleton of Megalodon. Sharks are made mostly of cartilage, not bone, so most of their body doesn't fossilize well. What we do have are their enormous teeth, thick, strong, and serrated like knives, which give us clues about their size and power. Scientists still debate what Megalodon actually looked like. Some think it had a thick, bulky body, while others imagine it with a more stretched out, streamlined shape. Estimates of its length range from about 14 metres to as much as 24 metres. That's roughly 47 to 80 feet. But most adult megalodons, based on studies of growth stages from juveniles to full-grown individuals, probably averaged around 10.5 metres long, or 34 feet. Its bite was terrifying. With jaws big enough to crush a car, Megalodon could chomp down with a force between 108,000 and 182,000 newtons. That's about 24,000 to 41,000 pounds of pressure. Its powerful teeth and jaws were built not just for cutting through flesh, but for shattering bones. Megalodon was not just huge, it was also everywhere. Fossils of its teeth have been found on every continent except Antarctica, which means it had a global or cosmopolitan range. It ruled the warm, open seas and likely played a major role in shaping the structure of marine ecosystems. This ancient shark hunted some of the largest creatures of its time: whales, seals, and even giant sea turtles. Unlike the modern great white shark, which tends to sneak up and bite its prey's soft underbelly, Megalodon likely used its brute strength to crash straight through the ribcage of the large animals, aiming to pierce the heart or lungs with a single devastating bite. Young megalodons were born in warm coastal waters, which served as safe nurseries. These juveniles likely fed on smaller whales and large fish, until they were strong enough to venture into deeper waters and hunt bigger prey. Megalodon didn't just vanish overnight. As the climate cooled during the beginning of the ice ages, the oceans changed. Sea levels dropped, which likely destroyed many of the warm, shallow coastal areas that baby megalodons needed to grow up safely. At the same time, their prey, especially baleen whales, began moving toward colder polar waters, far from the tropical zones where Megalodon thrived. To make things worse, powerful new predators were rising in the oceans. These included macroraptorial sperm whales, like Leviathan, and possibly early ancestors of killer whales. These competitors may have hunted similar prey, and made survival even harder for the already struggling Megalodon. All of these pressures, changing climate, shrinking nursery grounds, shifting prey distributions, and growing competition, combined to push Megalodon toward extinction. Although some early fossil evidence had suggested Megalodon survived into the Ice Age, most modern studies now agree it likely disappeared around 3.6 million years ago. Megalodon may be gone, but its teeth have fascinated humans for thousands of years. These enormous razor-edged fossils have been dug up since ancient times and used in all sorts of ways. In the Americas, long before European contact, indigenous cultures treasured Megalodon teeth for their size and shape. They turned them into sharp tools, jewellery, weapons, and even ceremonial items. In Panama, people from the ancient Sitio Conte culture used these teeth in important rituals and burials. As far back as the year 430 before the Common Era, Algonquin peoples near the Chesapeake Bay were mining megalodon teeth and trading them with the Adena people in what is now Ohio. These fossils were valuable long before their true origin was known. In ancient Rome, the writer Pliny the Elder described these strange triangular stones in the year 73 of the Common Era. He called them glossopetrae, or tongue stones, because they looked like petrified human tongues. Roman folklore said they fell from the sky during lunar eclipses. By the 12th century, a legend from Malta claimed these stones were actually the tongues of serpents turned to stone by St. Paul the Apostle. People believed they had the power to neutralize poisons. This belief spread throughout Europe during the Middle Ages and Renaissance. Nobles carried these stones as protective charms, and some even made dishes out of them, thinking they could purify food and drink. By the 16th century, megalodon teeth were even ground up and used in medicines called Goa stones, believed to cure illness and ward off evil. Though some people had begun to suspect that glossopetra were actually fossilized shark teeth as early as the year 1554, it was not until the early 17th century that serious scientific arguments were made. Italian naturalist Fabio Colonna published a drawing in the year 1616 comparing a megalodon tooth from Malta with a great white shark's. He believed their similarities proved they were both shark teeth, not petrified tongues. Colonna even burned a sample of a glossopetra to prove it came from an organic material, like bone or tooth. Still, many people doubted this theory, especially since megalodon teeth were sometimes found far inland, far from the sea. It wasn't until later scientists such as Robert Hooke and John Ray in England, and Niels Steensen, known as Nicholas Steno, in Denmark, revisited the theory in the late 17th century that it gained wider acceptance. Steno, in particular, made an important contribution. In the year 1666, a great white shark was caught, and he dissected its head. A year later, in 1667, he published engravings comparing the shark's teeth to fossilized megalodon teeth. While the illustrations were not of the actual shark he examined, he reused earlier drawings created in the 1590s. They still helped make his case. Steno also proposed a geological explanation for why shark teeth were found far from oceans. The land must have once been underwater and later uplifted by geological forces, leaving marine fossils behind. For a long time, Megalodon was classified as a close relative of the great white shark in the genus Carcharodon. This was because their teeth look somewhat alike, but more recent evidence shows that this similarity is likely due to convergent evolution, where unrelated animals evolve similar features to deal with similar challenges. Today, Megalodon is placed in the genus Otodus, within the extinct family Otodontidae. The great white shark, meanwhile, is more closely related to the extinct broad-toothed mako shark, Cosmopolitodus hastalis, as shown by finer details in their teeth. Their shared ancestor probably lived about 4 million years ago. The group of ancient sharks known as Carcharocles includes 4 different species: Carcharocles auriculatus, Carcharocles angustidens, Carcharocles chubutensis, and the most famous one of all, Carcharocles megalodon, often simply called megalodon. Over time, these sharks evolved in fascinating ways. Their teeth slowly changed shape. The serrations along the edges became sharper and more pronounced. The crowns of the teeth grew wider, and the teeth themselves took on a more triangular form. Alongside these changes, the small pointed side cusps, or lateral cusplets, gradually disappeared. These changes didn't happen overnight. It took roughly 12 million years for the transition from C. chubutensis to C. megalodon to be complete. These evolving teeth give scientists clues about how these sharks hunted. Early species probably used a grasping and tearing bite to catch fast-moving fish. But as time passed, their bite evolved into a more powerful slicing type, ideal for attacking larger prey like whales and dolphins known as cetaceans. The genus Carcharocles was first proposed in the year 1923 by 2 scientists, D.S. Jordan and H. Hannibal, who created the category to include C. auriculatus. Later, during the 1980s, researchers decided that Megalodon also belonged in this genus. However, the story of how these sharks are named and grouped gets even more complicated. In the year 1960, a French shark expert named Edgard Cassier introduced a different genus called Procarcharodon, which included all 4 of these ancient sharks and separated them from the modern great white shark. Later, scientists decided that Procarcharodon was actually the same as Carcharocles, and so they treated the older name as the correct one. Cassier also introduced another genus called Paleocarcharodon, which he believed was the earliest ancestor of this shark group. According to one theory, Paleocarcharodon might have been the shared ancestor of both Megalodon and the great white shark. But not all scientists agree. Some think that Paleocarcharodon was a side branch of evolution that didn't lead to Megalodon at all. Another idea about how Megalodon evolved is that it came from an older shark called Otodus obliquus, which lived during a long stretch of time, from the Paleocene epoch, about 60 million years ago, to the Miocene epoch, around 13 million years ago. This shark may have evolved into Otodus axuaticus, which then gave rise to Carcharocles auriculatus, followed by C. angustidens, then C. chubutensis, and finally the mighty megalodon. This version of the evolutionary tree traces everything back to a shark from the Cretaceous period called Cretalamna, making Otodus the starting point for the whole lineage. Still, some scientists think these sharks weren't separate species at all. In 2001, paleontologist Michael Benton suggested they were all just different stages of the same species slowly changing over millions of years, a concept known as a chronospecies. In this view, C. auriculatus, C. angustidens, and C. chubutensis were not truly separate, but just different time-based versions of one shark species. Some experts even suggest putting all of them under the genus Otodus, and leaving Megalodon as the only true member of Carcharocles, if that genus is even valid. In fact, some researchers believe that Megalodon should not be in the genus Carcharocles at all, but instead placed in Otodus, making its full name Otodus megalodon. Back in 1974, a scientist named Henry Capetta introduced the subgenus Megaselicus, calling the species Otodus, Megaselicus, megalodon, and Otodus, Megaselicus, chubutensis. Then, in 2006, Megaselicus was considered a separate genus altogether. In 2016, the discovery of fossils from a shark called Megalolamna caused scientists to re-examine the whole classification. They concluded that Otodus, as previously defined, was paraphyletic, meaning it left out some of its descendants. By adding Megalodon and its relatives into Otodus, the group would become monophyletic, including all direct descendants of a common ancestor. In this structure, Megalolamna would be the sister group. As for what Megalodon looked like, there are 2 main ideas. One is that it had a stocky, muscular body similar to a great white shark, but even more robust. Its jaws may have been wider and more rounded, and it likely had small, deeply set eyes, giving it a pig-eyed appearance. Its fins probably looked like those of a great white, but thicker due to its enormous size. Another idea is that Megalodon looked more like a whale shark or a basking shark. In this model, it had a crescent-shaped tail, small second dorsal and anal fins, and a special structure called a caudal keel, a ridge on both sides of its tail that helps reduce water resistance. This streamlined design is common in large, fast-swimming animals like tuna and whales. The head shape might have varied, but the drag-reducing features were mainly in the back half of the body. In 2024, a new idea was put forward, suggesting that Megalodon's body was longer and more stretched out than people previously thought. This idea was supported in 2025 by a study led by Shimada and colleagues, who compared the proportions of Megalodon's skull and tail with those of other large sharks. They concluded that Megalodon might have grown even longer than scientists had estimated before. Because Megalodon is mostly known from fossilized teeth and vertebrae, its size has been hard to determine. Scientists usually compare these parts to those of the great white shark, since it's the closest living shark with a similar body plan. By doing so, they've come up with a range of size estimates. Depending on the method and the body shape assumed, the maximum total length of Megalodon has been estimated to be between 14.2 meters and 24.3 meters. A study from the year 1996 suggested that adult male megalodons might have weighed between 12.6 and 33.9 metric tons, and could have measured 10.5 to 14.3 meters long, that's about 34 to 47 feet. Adult females, which were likely larger, might have weighed between 27.4 and 59.4 metric tons and measured 13.3 to 17 meters long. That's about 44 to 56 feet. Another study from 2015, based on 544 fossil teeth from different places and times, found that most megalodons were around 10.5 meters long, but individuals range from as small as 2.2 meters to as large as 17.9 meters. For comparison, large great white sharks usually grow to about 6 meters, around 20 feet, though there are a few unconfirmed reports of even larger individuals. The whale shark, which is the biggest living fish today, can reach at least 15 meters in precaudal length, and possibly up to 18.8 meters in total length. It's also likely that megalodon populations in different parts of the world grew to different sizes and may have behaved differently depending on their local environments. No matter how you look at it, Megalodon was almost certainly the largest shark that ever lived, and one of the greatest ocean predators in Earth's history. In the year 2015, a group of scientists conducted a study to understand how the size of a shark is connected to how fast it usually swims. They estimated that the massive prehistoric shark known as Megalodon probably cruised through the oceans at around 18 kilometers per hour, which is about 11 miles per hour. This estimate was based on the assumption that a typical megalodon weighed about 48 metric tons, which equals roughly 53 short tons or 47 long tons. This swimming speed is actually quite similar to that of another gigantic sea creature, the fin whale, Balænoptera physalis, which usually travels at speeds between 14.5 kilometers per hour and 21.5 kilometers per hour, or about 9 to 13.4 miles per hour. Then, in the year 2022, a scientist named Cooper and his team refined these numbers using a new method. They looked at the shark's relative cruising speed, which means how many body lengths it could swim per second. They estimated that a megalodon measuring 16 meters would have an average cruising speed of 5 kilometers per hour, or about 3.1 miles per hour. This meant it moved faster in absolute terms than modern sharks in the lamnid family, but slower in relative terms when you account for body length, something that lined up with earlier studies. So why was Megalodon so enormous? Several reasons might explain this. One reason is the warm climate of the time, which may have allowed cold-blooded creatures to grow larger. Another reason was the availability of big prey. Megalodon had plenty of large animals to hunt and feed on. Yet another possibility is a special type of internal temperature control called regional endothermy, or mesothermy, where parts of the body stay warmer than the surrounding water. This ability could have helped Megalodon burn energy faster and swim more quickly, like modern fast-swimming sharks. Sharks in the otodontid family, to which Megalodon belonged, are usually thought to be cold-blooded or ectothermic, but this idea doesn't quite fit with what we know about Megalodon. The largest cold-blooded sharks alive today, like the whale shark, are filter feeders, meaning they swim slowly and feed on tiny organisms. But sharks that actively hunt large prey, like those in the lamnid family, are warm-blooded in specific regions of their bodies, which helps them maintain speed and power. Tooth chemistry, the need for powerful bursts of speed when hunting warm-blooded prey, and comparisons with modern predators all suggest that Megalodon was probably a regional endotherm too, meaning it kept parts of its body warm to stay fast and active. Then, in 2020, a researcher named Shimada and his colleagues proposed another reason for Megalodon's giant size: intrauterine cannibalism. This is a behaviour where the largest baby shark inside the mother eats its smaller siblings before birth. Over generations, this process could lead to bigger and bigger offspring, and mothers would have to grow even larger to carry them. This might also have increased their need for energy, encouraging the development of partial warm-bloodedness. Meanwhile, male sharks would have had to grow larger too, to be able to mate effectively with the giant females, probably using claspers, just like today's sharks do. The most common fossils we find of Megalodon are its enormous teeth. These teeth are easily recognizable. They are triangular, thick, strongly built, and extremely large. They have fine serrations along the edges but lack small side cusps, and they feature a V-shaped notch where the root connects to the crown. The way the teeth attach to the jaw is also interesting. They meet the jaw at a steep angle, like in today's great white shark, and are held in place by connective tissue fibres. The bottom part of the tooth is rough, which may have helped to hold it firmly in place. The side of the tooth facing the tongue, the lingual side, was curved outward, while the labial side, which faces the lips, was slightly curved or flat. The front teeth stood straight up and were symmetrical, while the teeth toward the back of the mouth leaned to the side and were asymmetrical. Some megalodon teeth are absolutely huge. Some measure over 180 millimeters in slant height, making them the largest known shark teeth ever found. In the year 1989, an almost complete set of megalodon teeth was discovered in Saitama, Japan. Another impressive set was found in the Yorktown Formation in the United States. These discoveries helped scientists reconstruct megalodon's jaw at the National Museum of Natural History. In 1996, scientists came up with a theoretical dental formula to describe megalodon's tooth layout. This formula means that megalodon had 4 different types of teeth: anterior, intermediate, lateral, and posterior. The intermediate tooth is especially interesting. It looks like a front tooth from the upper jaw, is symmetrical, and does not lean toward the centre of the mouth. It is referred to as a 3. Megalodon had a very strong and sturdy set of teeth, probably more than 250 teeth, arranged in 5 rows. Some large individuals may have had jaws that stretched nearly 2 meters wide, which is about 6.5 feet. The teeth were serrated like a saw blade, helping them slice easily through meat and bone. It's believed Megalodon could open its mouth to an angle of 75 degrees, and maybe even up to 100 degrees based on reconstructions. In 2008, a group of scientists led by S. Rowe tested the bite force of a great white shark using a specimen that was 2.5 meters long. They scaled up the results to estimate how powerful Megalodon's bite would have been. Depending on body mass estimates, they calculated a bite force ranging between 108,500 newtons and 182,200 newtons. That's between 24,400 pounds and 40,960 pounds of force. In comparison, the strongest confirmed bite for a great white shark is 18,200 newtons, around 4,095 pounds, and the ancient armoured fish Dunkleosteus had a bite force of about 7,495 newtons. Also, sharks tend to shake their heads while biting, which multiplies the damage they do. That means the actual impact on prey would have been even greater than the raw numbers suggest. As with all sharks, Megalodon's skeleton was made of cartilage, not bone, so most of its body didn't fossilise well. Still, we have remains such as teeth, vertebral centra, spinal discs, and coprolites, fossilised poop. To support its gigantic teeth, Megalodon would have needed very strong, heavy jaws, much thicker than those of the great white shark. Its skull, made of cartilage, would have looked more blocky and solid. Its fins were large and in proportion to its huge body. Some parts of the spine have been found too. The most famous example comes from Belgium, found in the year 1926, where paleontologists unearthed a partial spinal column containing 150 vertebrae, ranging in size from 55 mm to 155 mm in diameter. Some scientists think Megalodon may have had over 200 vertebrae, which is more than any other known shark. Only the great white comes close. Another specimen from Denmark, discovered in 1983, had 20 vertebrae, ranging from 100 mm to 230 mm across. Fossilised poop from Megalodon has also been found, especially in South Carolina, and it's shaped like a spiral. This suggests that Megalodon, like many modern sharks, had a spiral valve in its intestines, which helps with digestion. Scientists named Gottfried and his colleagues even reconstructed an entire skeleton of Megalodon, which is now displayed at the Calvert Marine Museum in the United States and the Isiko South African Museum. This model is 11.3 meters long, about 37 feet, and represents a fully grown male, based on what we know about how great white sharks grow and change as they age. Helicoprion, whose name means spiral saw, was a strange and fascinating fish that lived in the ancient oceans hundreds of millions of years ago. It belonged to a group of extinct fish called Eugenodontiforms, which were distantly related to today's chimeras, deep-sea creatures sometimes called ghost sharks. However, Helicoprion looked nothing like its distant cousins. This bizarre creature had a body made mostly of cartilage, much like modern sharks and rays. Unfortunately, cartilage does not fossilize very well, so most of what we know about helicoprion comes from one part of its body, the incredible spiral of fused teeth found in its lower jaw. These tightly curled clusters of teeth are known as tooth whorls, and they look like a circular saw blade. Scientists believe that this spiral of teeth was perfectly designed for slicing into soft-bodied animals like squid. It may have also helped crush the shells of harder prey, such as ammonites and nautiloids, which were common in those ancient seas. In the year 2013, scientists studied the shape and structure of these tooth spirals using a method called morphometric analysis. They concluded that the genus Helicoprion included only 3 species: H. devesi, H. bisonoi, and H. ergasamenon. Fossils of Helicoprion have been discovered all around the world, including places like Russia, Western Australia, China, Kazakhstan, Japan, Laos, Norway, Canada, Mexico, and several states in the United States such as Idaho, Nevada, Wyoming, Texas, Utah, and California. These fossils come from rocks that are between 290 million and 270 million years old, dating back to a time known as the Permian period. Over half of all Helicoprion fossils belong to H. devesi and were found in Idaho, especially in an ancient rock formation called the Phosphoria Formation. About a quarter of the fossils come from the Ural Mountains in Russia and belong to H. besonoi. Since most of the skeleton was made of cartilage and decayed quickly after death, it is very hard to know exactly what the entire fish looked like. However, by comparing it with its close relatives like Casaeodus, Fadinia, and Romarodus, which lived from the Pennsylvanian to the Triassic periods, scientists have made some educated guesses. These related fish had long, torpedo-shaped bodies built for fast swimming. They had large triangular dorsal fins and forked tails, similar to modern fast-swimming ocean hunters like tuna, swordfish, and great white sharks. Unlike most modern fish, they lacked pelvic and anal fins, and one genus, Romeridus, had long ridges, or keels, along the sides of its body for added stability. Some also had 5 to 6 gill slits, like primitive sharks. Based on the size of the tooth whorls, scientists believe that some individuals of Helicoprion could grow to be between 5 and 8 meters long. That's about the size of a modern basking shark. One gigantic tooth whorl, found in a specimen labelled IMNH 49382, measured 56 centimeters in diameter and likely belonged to a fish over 7 meters long. Each tooth whorl consisted of dozens of sharp teeth arranged in a spiral. The youngest tooth sat at the center of the spiral and was hooked in shape. As the fish grew, new triangular teeth were added to the outer edge of the spiral, becoming larger with each new layer. These teeth were not only sharp and serrated, but also carefully layered, with each tooth slightly overlapping the one behind it, like tiles on a roof. The most complete fossil ever found of Helicoprion is known as IMNH 37899, or Idaho 4. It was discovered in Idaho in the year 1950 and formally described in 1966. Then, in 2013, scientists used CT scans to look deep into the fossil without damaging it. What they found was astonishing: a nearly complete set of upper and lower jaws preserved in 3 dimensions. This incredible fossil included several important jaw structures: the palatar quadrates, which formed the upper jaw, Meckel's cartilages, which formed the lower jaw, and a special thick piece of cartilage supporting the tooth whorl called labial cartilage. All of these parts were mineralized, meaning they had hardened like bone and were covered in a kind of tough tissue similar to what is seen in today's cartilaginous fish. However, the part of the skull that would have held the brain and sensory organs, the chondrocranium, was missing. The preserved jaws were surprisingly narrow compared to modern sharks, although this might be partly due to being squashed over time after the animal's death. Helicoprion had a unique jaw structure known as autodiastylic suspension, where the upper jaw was attached to the skull at 2 different points. This setup is seen in some early fish, but is only found in embryos of modern chimaeras. Another unusual feature of Helicoprion's jaws was that the inside of the upper jaw was lined with small rounded teeth, forming a kind of pavement that scraped against the tooth whorl below. Even more amazing, Helicoprion had a special joint between the lower jaw and the labial cartilage that helped control how wide the jaw could close. This system probably protected the fish's skull from being damaged by its own sharp spiral of teeth during feeding. Some rare fossils from Kazakhstan, associated with H. besnoi, also preserve skin-like scales called odontodes, which are basically tiny tooth-like structures. These scales had cone-shaped crowns with sharp ridges and could either have one crown per base, monodontode, or several crowns fused together, polyodontode. Compared to other similar fish, the scales of helicoprion were more sharply pointed and possibly gave it a more hydrodynamic shape. The strange spiral-shaped tooth arrangement found in helicoprion, called a tooth whirl, was not just for show. Its unique design, along with the fact that the teeth don't show much wear, suggests that this ancient sea creature fed mostly on soft-bodied animals. If it had tried to eat prey with hard shells, they likely would have just slipped out of its mouth, because its teeth weren't built for crushing or grinding. Its jaw was also quite narrow, so helicoprion probably wasn't very good at sucking prey into its mouth like some modern fish do. Instead, scientists believe it was a bite feeder, meaning it had to actively chomp down on its food. A study by Ramsey and his team in the year 2015 used computer models to explore how this worked. They found that the teeth in the whirl had different jobs depending on where they were placed along the spiral. The teeth at the front helped catch prey and pull it deeper into the mouth. The ones in the middle were sharp and acted like spears, and the back teeth helped pierce the prey and push it down the throat. The prey would get pressed between the spiral of teeth and the two sides of the upper jawbones. A piece of cartilage on the lip, called the labial cartilage, helped support the whirl and keep it steady during feeding. Scientists believe that when helicoprion attacked its prey, it opened its jaws wide at first, then used quick, smaller jaw movements to move the prey farther into its mouth, just like how some modern sharks do today. While today's sharks often shake their heads side to side to saw through their prey, helicoprion may not have needed to. As its jaws opened, the curved front teeth probably sliced through the prey in a slashing motion, much like a knife cutting through meat. It likely used a series of fast, powerful bites to grab and shove its prey deep into its mouth, then kept rhythmically opening and closing its jaws to help cut through it. Ramsey and his colleagues also proposed another interesting idea, that the spiral tooth whirl could have helped helicoprion deal with animals that had hard shells, like ammonoids and nautiloids, which were common in the oceans of the early Permian period. If helicoprion bit one of these shell-covered animals from the front, the whirl might have pulled the soft body out of the shell and into the mouth. During these bites, the structure of the jaws and teeth formed a system like an upside-down version of a three-point bending test, a method used in engineering to measure force. This setup helped trap and hold onto soft parts while also giving extra strength to bite through tougher shells. At the points where the prey was gripped, the estimated force of the bite ranged from about 1,192 to 2,391 newtons. That's roughly 268 to 538 pounds of force. The pressure applied at first contact with prey may have ranged from about 397 to 797 million newtons per square metre, or about 57,600 to 115,600 pounds per square inch. With a bite that strong, helicoprion may have been able to eat not only soft-bodied creatures, but also bony fish and other cartilaginous fish that didn't have heavy armour or thick bones. Detailed studies of a well-preserved skull known as specimen IMNH 37899 show several features that help place helicoprion within a group of cartilaginous fish called Euchondrocephali. One key feature is its autodiastolic jaw suspension, meaning the upper jaw was not directly connected to the skull through a separate bone called the hyomandibular, which is common in other sharks and rays. Euchondrocephali is an ancient group that is mostly extinct today. The only surviving members belong to a small order called chimeriforms, which are part of a subclass known as holocephali. These deep-sea fish are commonly called chimeras or ratfish. Although helicoprion and these modern chimeras are only very distantly related, scientists had suspected a connection for a long time based on similarities in their unusual tooth structures. More specifically, helicoprion belonged to a group of prehistoric fish called Eugeniodontida. These shark-like creatures lived from the Devonian period to the Triassic period. That's roughly from over 400 million to around 200 million years ago. Eugeniodonts had simple skulls with very few side teeth, but they did have large spirals of blade-like teeth right in the middle of their lower jaw. Within this group, helicoprion is placed in a subgroup called Edistoidea. Members of this subgroup are known for having especially tall and slanted teeth at the jaw's centre. The Edistoidea are further split into two families based on tooth style. One family, called Edistidae, had shorter tooth blades that pointed backward. The other family includes helicoprion. Some scientists refer to this group as Agassizodontidae, named after another genus called Agassizodus. However, many others prefer the older name Helicoprionidae, which had already been in use for about 70 years before Agassizodontidae was suggested. Fish in this family, whether you call them helicoprionids or Agassizodontids, had large arch-shaped tooth spirals supported by cartilage. Unlike modern sharks, they didn't shed their teeth. Instead, their whorls kept growing, constantly adding new teeth that leaned forward at the top of the spiral. Because most eugeneodontid fossils are just broken pieces of these tooth spirals, it's still difficult for scientists to clearly figure out how all the species are related to one another. Even so, each discovery brings us closer to understanding these mysterious, ancient sea predators. More than 500 million years ago, long before the time of the dinosaurs, Earth's oceans were teeming with strange and alien-looking creatures. One of the most remarkable and mysterious of these animals was Anomalocaris, a name that comes from ancient Greek and means unusual shrimp. But make no mistake, this wasn't your average sea creature. Anomalocaris was unlike anything alive today. It had a soft, segmented body lined with flapping lobes, large, bulging compound eyes like those of modern insects, and a pair of powerful claw-like arms jutting out from its head, perfect for grabbing prey. Anomalocaris belonged to a group of animals known as radiodonts, an early branch of arthropods, the same massive family that includes today's insects, crabs, spiders, and lobsters. These creatures were some of the earliest predators in the history of life, and Anomalocaris was among the biggest and baddest of them all. Some individuals are believed to have grown as long as 34 to nearly 38 centimetres. That's around 13.5 to nearly 15 inches, not including their grabbing arms or tail fins. In the Cambrian period, that made Anomalocaris a true giant, and very likely an apex predator, meaning it ruled the food chain in its environment. The story of how scientists discovered Anomalocaris is almost as strange as the creature itself. Back in the year 1886, a geologist named Richard G. McConnell from the Geological Survey of Canada set out to explore fossil-rich rocks in the Stephen Formation, high up on Mount Stephen in what is now British Columbia, Canada. On the 13th of September, he climbed the mountain and found many fossilised trilobites, along with two strange specimens that no one could identify. Several years later, in August of 1891, another fossil collector named Henri Marcami gathered 48 more of these odd fossils from the same location. That made a total of 50 mysterious fossils. In 1892, paleontologist Joseph Frederick Whiteaves examined the specimens and came to a conclusion. He thought they were the abdomens of an extinct type of shrimp-like crustacean. He gave them the scientific name Anomalocaris canadensis, meaning the unusual shrimp from Canada. He based the name on how strange the body parts looked, flattened sideways, shaped oddly, and with unusual spiny structures sticking out from their sides. In the year 1928, a Danish paleontologist named Kai Henriksen thought he had solved the mystery. He proposed that another fossil from the same rock formation, called Tuzoia, which was known only from its protective shell, might be the missing front half of Anomalocaris. Artists began drawing Anomalocaris based on this idea, imagining it as a shrimp-like creature with Tuzoia's shell and Anomalocaris' spiny rear segments. What no one realised at the time was that various body parts from Anomalocaris and its relatives had been found, but scientists kept mistaking them for different animals. For instance, the creature's circular mouth, which looked like a ring of plates with jagged edges, was found by the famous paleontologist Charles Doolittle Walcott, but he thought it was a jellyfish and called it Peytoia. Walcott also discovered one of the claw-like frontal arms, but he believed it was the tail or feeding limb of a different animal named Sydneyia. He wasn't alone in his confusion. In the same paper where he named Peytoia, Walcott also described a fossil he called Legania, which he thought was a sea cucumber, a type of soft-bodied marine animal. In reality, all three of these names, Anomalocaris, Peytoia and Legania, were actually based on different parts of the same kind of animal. Fast forward to the year 1966, when the Geological Survey of Canada launched a massive project to re-examine the Burgess Shale, one of the most important fossil sites on Earth. Leading the effort was British paleontologist Harry B. Whittington, along with his students Simon Conway Morris and Derek Briggs. At first, they too added to the confusion. In 1978, Conway Morris realised that the mouth of Legania was identical to Peytoia, and guessed that Legania was a composite fossil, a mix of parts from different animals. In 1979, Briggs concluded that the so-called body segments of Anomalocaris were actually front limbs, and that Walcott's feeding arm was a matching appendage from a similar creature, which they nicknamed Appendage F. Then came a moment of revelation. While examining what appeared to be just another unrelated fossil, Whittington carefully removed a layer of stone and discovered that the frontal limb, mouth and body were all connected. This was a single animal, not three different ones. It took a few more years of research and debate, but eventually scientists realised that all these parts, Anomalocaris, Peytoia, Legania and Appendage F, belonged to one group of giant swimming predators, now classified under the order Radiodonta. Even though Peytoia was named first and takes precedence in naming the full animal, the name Anomalocaris is still used for a larger distinct species, keeping its own genus name. As more fossils were found in other parts of the world, the Anomalocaris family tree grew more complex. In the year 2011, fossilised compound eyes from Anomalocaris were discovered in Emu Bay Shale on Kangaroo Island, Australia. These eyes proved that Anomalocaris really was an arthropod, and also showed that complex vision evolved long before jointed legs or hard exoskeletons. The fossil turned out to be a new species, now called Anomalocaris delae. Over time, more and more fossils that had once been lumped into the Anomalocaris category were found to belong to other genera. In the year 2021, two species originally called Anomalocaris sarin and Anomalocaris magnabasis were moved into a new genus called Heucharis, though later studies suggested that these species actually belong to different families altogether. That same year, another species, Anomalocaris pennsylvanica, was moved into a new genus called Lenisocaris. Then, in 2022, a well-preserved fossil known as ELRC 20001, which had been thought to be part of Anomalocaris or a complete Asaron, got a new name, Innovasiocaris. And in 2023, Anomalocaris kunmingensis was reclassified as Guanchancaris, while another species, Anomalocaris briggsii, was renamed Echinocaris. Anomalocaris was one of the biggest and most fearsome creatures of its time, living hundreds of millions of years ago during the Cambrian period. Compared to the other animals that lived in the oceans back then, it was a true giant. One of the best preserved examples of Anomalocaris canadensis, labelled as specimen ROMIP 51211, measured up to 20.5 centimetres long, about 8.1 inches. If you don't count its large front limbs and the wide fan at the end of its tail, its body alone was about 17.5 centimetres long, around 6.9 inches. Just one of its large, spiny front limbs could stretch as long as 18 centimetres. That's around 7.1 inches. Scientists estimate that a full-grown Anomalocaris canadensis could have reached a body length of between 34.2 and 37.8 centimetres, about 1.1 to 1.2 feet. Again, not including the frontal limbs or the tail fan. There were earlier guesses that Anomalocaris might have grown up to 1 metre, over 3 feet, long. But when experts looked more closely at how its body parts were proportioned, they found this was unlikely. For instance, the body was usually just twice as long as the front limbs, which made such a huge size less probable. A different species called Anomalocaris delae, which was once thought to be just a type of canadensis, lived in what is now Australia, in a fossil site called the Emu Bay Shale. It may have been even bigger than canadensis. One of its front limbs measured 18.3 centimetres long, around 7.2 inches. This suggests that the whole animal could have been anywhere from 34.8 to as much as 51.2 centimetres in length. That's about 1.1 to 1.7 feet. Anomalocaris moved through the ocean with surprising grace for such a strange-looking creature. It had soft, flexible flaps running down each side of its body. These flaps overlapped in such a way that each one sat slightly underneath the one behind it. This clever design allowed the flaps to work together like a single long fin, helping the animal glide smoothly through the water. Scientists even built a remote-controlled model to test how it swam. The results showed that Anomalocaris was naturally stable in the water. That means it didn't need a big or complicated brain to stay balanced while swimming. Its body was widest around the third to fifth pair of flaps and got narrower toward the tail. At the base of its head, near the neck, were 3 pairs of smaller flaps. Counting how many flaps were near the tail is tricky because they tend to blend together, but in the main part of the body, Anomalocaris canadensis had 13 pairs of these swimming flaps. One of the strangest and most interesting parts of Anomalocaris was its round, plate-covered mouth, often called the oral cone. The mouth was made up of several hard plates arranged in a circle with a 3-way or triradial symmetry. 3 of these plates were large, and between each of them were 3 or 4 medium-sized plates. Scattered among them were smaller plates. Many of these plates were wrinkled and had tiny scale-like bumps near the centre of the mouth. This mouth looked nothing like the smoother 4-way tetraradial mouths seen in some of its relatives like Pitoia and Herdia. Like other members of its group, Anomalocaris had protective plates on its head called sclerites. There were 3 of them. The one on top, known as the head shield or H-element, was shaped like an oval stretched sideways and had a clearly defined rim around its edge. On either side of the head were 2 more oval plates called P-elements, connected by a thin bar-like structure. For a long time, scientists thought these side plates were actually huge compound eyes, but they later discovered that wasn't the case. The real eyes of Anomalocaris were located on stalks and were extremely advanced, especially for a creature that lived over 500 million years ago. Fossils from the Emu Bay Shale show that Anomalocaris delayei had eyes that were 30 times sharper than those of trilobites, which were once considered the best-eyed animals of that era. In one fossil, a single eye had over 24,000 lenses, and the eye itself was about 3 centimeters, or 1.2 inches wide. That kind of resolution would have been close to the vision of today's dragonflies, which have around 28,000 lenses per eye. There is also evidence that Anomalocaris could see in at least 2 different colours, meaning it may have had dichromatic colour vision, a rare trait among early animals. At the back of its body, Anomalocaris had a large tail fan made up of 3 pairs of wide, fin-shaped lobes on each side and 1 central lobe at the very end. At first, scientists believed this fan helped push it forward through the water, but newer research shows the tail might have been more important for steering rather than speed. Its gills were also unusual. Instead of being flat or leaf-like like modern gills, they were long and hair-like, called lanceolate blades. These gill filaments were arranged in rows along the body, forming what are known as cetal blades. Each body segment had 2 of these blades attached to its top side, and a line down the middle separated them into 2 sides. These thin structures helped the animal absorb oxygen from the water. Probably the most iconic part of Anomalocaris was its pair of large frontal appendages, which were attached to the front of the head just before the mouth. These limbs looked a bit like spiny arms or claws, and each one was made up of 14 segments, called pedomeres. The first segment formed the base or shaft, and the remaining 13 made up the flexible part. Each segment had a pair of downward-pointing spines called endites. These endites weren't smooth. They were covered with many smaller spines that stuck out from both the front and back edges. With these spiny, barbed arms, Anomalocaris could snatch prey and guide it straight into its powerful circular mouth. The idea that Anomalocaris was a fast and powerful hunter has been widely supported by scientists for many years. In fact, many researchers believe it was one of the very first top predators to ever live on Earth. This ancient creature had large, claw-like frontal appendages, which were like spiky arms near its mouth, that looked perfectly built for grabbing and catching prey. Inside its body, it also had mid-gut glands, which are similar to digestive organs in today's predators. These features all point toward a meat-eating lifestyle. One species in particular, Anomalocaris canadensis, stood out among the creatures of the famous Burgess Shale, a fossil site in what is now Canada. A. canadensis was enormous compared to its neighbours in that ancient ocean, and it likely sat at the very top of the food chain around 505 million years ago. For a long time, scientists believed that Anomalocaris used its strong mouth parts to attack and eat hard-shelled animals like trilobites, those armoured creatures that looked like a mix between a beetle and a horseshoe crab. But more recent studies have started to question that idea. Some researchers now think that Anomalocaris may have focused only on soft-bodied animals, ones without tough shells or armour. That would make its hunting much easier and less damaging to its own body. Interestingly, some trilobite fossils from the Cambrian period have been found with round or W-shaped marks that look like bite wounds. At first, people thought these bite marks came from Anomalocaris, especially since they seem to match its circular mouth parts. But it turns out those marks are more likely from a different creature called Predatory, which was once mistakenly thought to be part of Anomalocaris. More solid evidence suggesting that Anomalocaris may have eaten trilobites comes from something called coprolites, which are fossilised pieces of ancient poop. Some of these coprolites are huge and contain bits of trilobite shells. Because Anomalocaris was one of the only animals from that time big enough to produce such large droppings, it's been suggested that it might have eaten them. However, there's a problem with this idea. Anomalocaris did not have hard or mineralised body parts, especially in its mouth. That makes it unlikely that it could crunch through the hard, calcified exoskeletons of trilobites. Because of this, scientists think those fossilised droppings might have been left behind by other creatures, perhaps even trilobites themselves, like those in the genus Redlichia, which may have been cannibalistic or scavenged the dead. Another interesting theory suggests that Anomalocaris used a clever technique to crack open its prey. It may have grabbed one end of a soft-shelled animal with its circular mouth, called an oral cone, while violently shaking the other end back and forth with its frontal appendages. This rocking motion could have caused the animal's outer shell to split or break apart at its weak points, giving Anomalocaris access to the softer insides. This strange feeding behaviour might have even pushed some early creatures like trilobites to evolve the ability to roll up into a ball so they wouldn't break when twisted or flexed. Yet, when scientists looked closely at the mouthparts of radiodonts, the larger group that includes Anomalocaris, they noticed something surprising. There was very little damage or wear on these parts. This means they probably didn't often bite into hard-shelled prey. If Anomalocaris had tried to eat too many armoured creatures like trilobites, its mouth would likely have been damaged or broken. Instead, its feeding tools seem more suited for suction feeding, pulling small, soft animals into its mouth much like a vacuum. Some scientists once thought A. canadensis might have been able to eat tougher animals because its front appendages had short, strong spines. But this theory mostly comes from comparing it to other radiodonts that had very delicate, feather-like limbs used for filter feeding, such as Echinocaris and Heucaris. When scientists examined the sharp gripping structures called endites on the arms of A. canadensis, they found almost no damage, except for a single fossil. This suggested that these limbs weren't regularly used to grab hard-shelled creatures. The shape of its mouth also tells us something important. While Predatory had a more rectangular oral cone with small outward-pointing spines, perfect for grabbing, A. canadensis had a more irregular, smaller opening. This kind of mouth likely didn't have a strong bite, but would have been good for sucking in soft prey. To further understand how Anomalocaris hunted, scientists used three-dimensional models of its frontal appendages. These digital tests showed that A. canadensis was well equipped to chase and catch small, fast-swimming, soft-bodied animals that were between about 2 to 5 centimeters wide. Some examples of its likely prey include creatures like Vetulicolians, free-swimming arthropods such as Isoxids and Hymenocarines, and the mysterious Nectocaris. A study in the year 2023 led by Bicknell and his team carefully examined the arms of Anomalocaris. They suggested that it was not only a predator, but an active swimmer, an ectonic hunter, meaning it lived and hunted in the open waters, not near the seafloor. When it stretched its limbs forward while swimming, it could have moved swiftly through the water, much like modern water bugs that dart across ponds and streams. Its large, complex eyes were probably perfect for spotting prey in bright, shallow waters. Because there were so many different kinds of soft, floating animals in the Cambrian seas, Anomalocaris had plenty of options to hunt. It likely avoided bottom-dwelling creatures like trilobites, not just because of their armour, but also because grabbing them from the ocean floor could have damaged its limbs on the rocky or muddy ground. Instead, other predators probably ruled the ocean floor. These included other types of radiodonts like Herdia, Cambrorista, Titanocaris, and Stanleycaris, as well as creatures known as arthropods, such as Sydneya. These animals were more adapted to life on the seabed and could feed on the hard-shelled or buried animals living there. Dunkleosteus was a massive and fearsome prehistoric fish that lived in the open oceans during the late Devonian period, around 382 million to 358 million years ago. This ancient creature belonged to a group of early-jawed fish called arthrodires, which means jointed neck. Dunkleosteus was one of the very first top predators to appear in any ecosystem on Earth, dominating the seas long before dinosaurs ever existed. Fossils of this incredible animal have been discovered in several parts of the world, including the United States, Canada, Poland, Belgium, and Morocco. Altogether, scientists have named at least 10 different species in the Dunkleosteus genus. These include Dunkleosteus torelli, belgicus, denisoni, marsaesi, magnificus, missouriensis, newberryi, amblyodoratus, raveri, and tudorensis. However, not all of these names may be valid, as some of the fossils are too incomplete or too similar to others. The most famous and best understood is Dunkleosteus torelli, which is also the type species, the one that defines the group. Although we don't know exactly what the full body of D. torelli looked like, paleontologists have tried different ways to estimate its size. The largest fossil ever found suggests it could have grown to between 4 meters and 10 meters long. That's about 13 to 33 feet. But more careful and recent studies say that most adult D. torelli were around 3.4 meters long, about 11 feet, while the biggest individuals may have reached up to 4.1 meters. As for its weight, it may have tipped the scales anywhere between 1 and 4 metric tons. That's about as heavy as a modern rhinoceros or even a small elephant. One of the most amazing things about Dunkleosteus is its jaws. It had powerful bladed jaws that it could open and snap shut incredibly fast, much like how some fish today suck in their prey by creating a vacuum. In fact, its bite was one of the strongest of any fish, alive or extinct, and among the most powerful ever recorded in the animal kingdom. With jaws like those, it could crush hard-shelled prey, such as armoured fish and ancient squid-like creatures. The story of Dunkleosteus begins in the year 1867, when a man named J. Terrell, who owned a hotel and loved collecting fossils in his free time, found the first pieces along the cliffs near Lake Erie, close to his home in Sheffield Lake, Ohio. Terrell donated these fossils to the Ohio Geological Survey, and in the year 1873, geologist John Strong Newberry gave the creature its first scientific name, Dinichthys hirseri. But as more fossils were found, especially in the Cleveland Shale, a layer of rock younger than the Huron Shale where Dinichthys hirseri was discovered, it became clear that there were actually several different large fish involved. In the year 1875, Newberry gave a new name to the more common fossil found in the Cleveland Shale, Dinichthys torelli, in honour of J. Terrell. Unfortunately, most of Terrell's original fossil collection was lost in a fire that same year in Elyria, Ohio. Later research showed that Dinichthys torelli was different enough from Dinichthys hirseri to belong in its own separate genus. In the year 1956, a paleontologist named Jean-Pierre Lehmann renamed the fish Dunkleosteus, combining the last name of David Dunkel, a vertebrate fossil expert at the Cleveland Museum of Natural History, with the Greek word for bone. The name literally means Dunkel's bone. Today, the Cleveland Museum of Natural History holds the largest collection of Dunkleosteus fossils in the world. The most complete and famous fossil, known as CMNH 5768, is proudly displayed there. Casts and replicas of this impressive fossil can also be seen in museums around the world, including the American Museum of Natural History, the Smithsonian National Museum of Natural History, the L. Peabody Museum, the Natural History Museum in London, and the Cincinnati Museum Centre. At first, scientists thought Dunkleosteus belonged to the same family as Dinichthys, but newer studies using more advanced techniques revealed that they were part of different branches of the Arthrodire family tree. In the year 2010, researchers Carr and Halavin grouped Dunkleosteus with a new set of relatives, placing it in its own family called Dunkleosteidae. Meanwhile, Dinichthys remained in a separate group known as Aspenothoracidae. In later studies, such as one from the year 2016, scientists used even larger datasets and proposed different family trees, casting some doubt on how Dunkleosteidae should be classified. As it stands, Dunkleosteus may still represent a mix of different species that have yet to be fully sorted out. In fact, many researchers now believe that the genus Dunkleosteus is a sort of wastebasket taxon, where large, heavily armoured fish fossils that don't clearly fit elsewhere have been lumped together. The type species, Dunkleosteus torelli, is still the biggest and best-known member of the group. Fossils of its skull alone can measure between 60 and 70 centimetres long, that's around 2 to 2.5 feet. These fossils have been found in late Devonian rock layers across the United States, especially in Ohio, Pennsylvania, Tennessee, California, and possibly Texas. Some remains have also been found in parts of Europe. As for the other species, some are known only from fragments and are less well understood. For example, Dunkleosteus belgicus was found in Belgium, but its fossils are so incomplete that some scientists think it may actually belong to a different genus called Ardenosteus. Another species, Dunkleosteus denisoni, is known from a small piece of its back armour and has features similar to D. marsaesi, another lesser-known member of the group. The species Dunkleosteus marsaesi refers to ancient fossil remains of Dunkleosteus found in the Atlas Mountains of Morocco. These fossils come from rocks laid down during the early part of the Furmenian stage, which is in the later part of the Devonian period, over 372 million years ago. This species is noticeably different from its famous cousin, Dunkleosteus torelli. For example, the average length of D. marsaesi skulls is about 35 centimetres, or roughly 1 foot and 2 inches. Unlike D. torelli, this species has a slimmer, narrower snout, and it might have had a unique feature called a postpineal fenestra, which is a small opening behind the pineal eye area. Even though D. marsaesi has some distinct features, many paleontologists believe it may actually be the same species as D. torelli. One researcher, Hans-Peter Schulze, has suggested it doesn't belong in Dunkleosteus at all, but rather in a closely related genus called Eismanosteus. Another species, Dunkleosteus magnificus, was a massive armoured fish that lived during the earlier Frasnian stage of the Devonian, found in the Rhine Street Shale of New York. This creature was first named Dinichthys magnificus by Hussakoff and Bryant in the year 1919. Later, in the year 1932, Heinz referred to it as Dinichthys mirabilis. Then, in the early 1970s, scientists Dunkel and Lane reassigned it to Dunkleosteus. However, not everyone agreed. Paleontologist Dennis Bryan believed it actually belonged to Eismanosteus. The skull of D. magnificus measures around 55 centimetres long, about 22 inches, and the entire fish is estimated to have reached about 3 metres in length, which is nearly 10 feet. The species Dunkleosteus missouriensis is known only from scattered fossil fragments found in Missouri, also from the Frasnian age. Dunkel and Lane believed these remains were almost identical to D. torelli. Later, in the year 1976, Levin reviewed the classification of these species and tentatively suggested that D. missouriensis might just be another example of D. torelli, labelling it Dunkleosteus cf. D. torelli, where cf means compare with. Dunkleosteus newberrii is primarily known from a jawbone called an infragnathal, which is about 28 centimetres long, or 11 inches. This fossil came from the Frasnian age rocks of the Genesee group in New York. When it was first discovered, scientists named it Dinichthys newberrii. In the year 2023, a group of researchers led by Lebedev noted that this species had an unusually long row of marginal teeth and lacked additional small tooth-like structures called accessory odontoids, which are common in other Dunkleosteus species. Because of these differences, they questioned whether D. newberrii even belonged in the Dunkleosteus genus, or its larger family group Dunkleosteoidea, at all. Then there's Dunkleosteus ambliodoratus, which is known from some fragmentary fossils found in rocks from the late Devonian in the Kettle Point Formation of Ontario, Canada. The species name means blunt spear, which refers to the way the skull bones at the back of the head, the nuchal and paranuchal plates, come together in a shape that looks like the head of a blunt spear. Another small species, Dunkleosteus reveri, may have only grown to be about 1 metre long, or just over 3 feet. It was discovered in a fossilised skull roof found inside a hard ball of limestone called a carbonate concretion in the lower part of the Huron Shale, part of the Furmenian strata in Ohio. One of the unique things about D. reveri is its relatively large eyes compared to its body size. Since its fossils are found in layers of rock just beneath those that contain D. terrelli, some scientists think that D. reveri might be an evolutionary ancestor of D. terrelli. The species is named in honour of Clarence Raver, a resident of Wakeman, Ohio, who discovered the first specimen. Dunkleosteus tudorensis is known from a jawbone found in the Belovo Formation of northwestern Russia, which dates back to the early to middle Furmenian stage. The species name honours the Marley Tudor River because the fossil was found on its bank. Although many species have been proposed, most scientists only accept 4 of them as true, valid species of Dunkleosteus. These are D. terrelli, D. reveri, D. tudorensis, and possibly D. amblyodoritus, even though the last is only known from a few pieces of bone that are hard to compare to others. The classification of earlier species from the Frasnian stage remains uncertain and controversial, while the later Furmenian species are much more clearly recognised as part of the Dunkleosteus genus. There are also additional unnamed Dunkleosteus fossils found in Furmenian rocks in California, Texas, Tennessee, and Poland. All known species of Dunkleosteus shared a common feature: thick, bony armour that covered the front part of their bodies. This armoured plating formed a kind of natural helmet around the head and shoulders. The thickest part of the armour, especially on the back of the skull, known as the nuchal plate, could be more than 5 to 7 centimetres thick, or about 2 to 3 inches. Elsewhere on the body the armour was much thinner, usually between about 1 and 2.5 centimetres, or 1/3 to 1 inch thick. These bones had a 2-layered structure, a hard outer shell and an inner spongy core very much like the bones of land animals today, and quite different from the thin, lightweight bones of most modern fish. Because only the front armoured sections of these fish were usually preserved, the rear part of the body, including the tail, remains a mystery. In fact, fewer than 5% of all Dunkleosteus fossils include more than 1/4 of the total skeleton. Because of this, scientists often use fossils of smaller, more complete placoderms, such as Cocosteus, as models when reconstructing what the rest of the body might have looked like. This has led to a wide range of size estimates for the larger species, Dunkleosteus terrelli. Dunkleosteus terrelli is believed to be one of the largest placoderm fishes that ever lived. Different researchers have estimated its full length to be anywhere between 4 metres, about 13 feet, and 10 metres, about 33 feet. However, most of these estimates are uncertain and lack clear explanations of how they were calculated. Often, the studies don't say which bones they measured, or how they scaled up from those bones to estimate the total body size. More careful studies that use detailed measurements suggest that a typical adult D. terrelli was about 3.5 metres long, roughly 11 feet, and that the very largest individuals may have reached just over 4 metres, or around 13 feet. These estimates are based on several methods, such as measuring the head length, the distance from the eyes to the gills, the size of the armour plates along the belly, and the placement of the fins. These different approaches all gave results in a similar range, lending confidence to their accuracy. Some estimates allow for larger sizes, up to 4.5 metres or 15 feet. But fish of that size would have very unusual proportions, especially in the size of the head compared to the rest of the body. Going beyond that size would make Dunkleosteus look quite unlike other armoured-jawed fishes, so such giant estimates are probably too high. On the other hand, lengths smaller than 3 metres are unlikely, because they don't match the size of the bones we've already found. Most scientific studies that use clearly defined methods have estimated that Dunkleosteus terrelli, the most famous species in its group, likely reached a body length of around 5 metres, that's about 16 feet, or even less. However, there is one exception, A study by Ferron and his team in the year 2017 suggested that Dunkleosteus might have been much larger. Their calculations, which were based on the size of the upper jaw in comparison to modern sharks, estimated a length between 6.88 and 8.79 metres, or about 22.5 to nearly 29 feet. Unlike today's sharks, Dunkleosteus and its relatives, called arthrodires, had proportionally much larger mouths. This means that using the jaw size to estimate body length the way we do for sharks doesn't work very well here. In fact, when the same method is used on another arthrodire called Cocosteus, it ends up exaggerating the fish's size. If we apply Ferron's calculations to actual fossil specimens, like the well-known CMNH 5768 specimen, it produces strange and unrealistic results, like a very small head and an extremely long, stretched-out body. This doesn't match what we know from the fossil record. When scientists correct the scaling to fit the actual fossils, Ferron's reconstruction suggests a total length of about 3.77 metres, which is around 12.5 feet. That falls right in line with the shorter and more widely accepted size estimates published in later research. In terms of weight, things get even more interesting. In the year 2010, a researcher named Carr estimated that an adult Dunkleosteus terrelli, measuring around 4.6 metres, might have weighed around 665 kilograms. That's 1,466 pounds, based on the typical body shape and weight of sharks. But a newer study from the year 2023 by Engelman took a different approach. He used a method based on volume, treating the body like an ellipsoid, a sort of squashed sphere, and came up with larger weight estimates. According to his research, a typical adult that measured about 3.41 metres would weigh somewhere between 950 and 1,200 kilograms. That's about 2,090 to 2,650 pounds. For the biggest individual in his study, which measured around 4.1 metres, the estimated weight was even more impressive, between 1,494 and 1,764 kilograms, or around 3,294 to 3,889 pounds. These heavier weights make sense because arthrodires were bulkier than sharks. They had wider and deeper bodies, which would have made them heavier for their length. An amazing fossil of Dunkleosteus terrelli was found with a preserved outline of the pectoral fin, the fins on the sides near the head, including structures called ceratotrichia, thin, stiff rods like those found in modern sharks. This fossil showed that the shape of the fins in ancient placoderms, the group Dunkleosteus belongs to, was much more varied than scientists used to think. The shape of these fins was likely influenced by how the fish swam, which reveals that locomotion played a big role in how their bodies evolved. Combined with the understanding that a fish's body shape is more influenced by how and what it eats than by its evolutionary relatives, this discovery helped researchers in 2017 figure out what Dunkleosteus's tail fin probably looked like. They proposed that it had a tail with a strong lower lobe and narrow base, called the caudal peduncle, and a high aspect ratio, a tail built for speed, unlike the eel-like tails earlier reconstructions had shown based on more primitive relatives. As for the backbone, only a small part of the vertebral column has been found. In a specimen named CMNH 50322, scientists discovered a series of 16 vertebrae located inside the trunk armour. Most of these bones are fused together and have large, sideways projecting joints, very different from what we see in other arthrodires. While many armoured fish show some fusion in the front part of the spine, called a synocual, Dunkleosteus is unique because this fused section stretches nearly all the way to the end of its trunk armour. This would have made the front part of its spine very stiff. Even more fascinating, there is a raised ridge inside the trunk armour, suggesting a powerful attachment point for a structure called the horizontal septum. This muscle structure would have helped transfer force from the strong trunk muscles to the tail fin. That means Dunkleosteus might have been built for fast and powerful swimming, similar to modern-day high-performance swimmers like tunas and mackerel sharks, also known as lamnids. The pelvic girdle, the bones that supported the pelvic fins near the rear of the fish, was surprisingly small when compared to the overall size of the armour. Several fossil specimens show these bones still in place, although their exact position wasn't recorded when the fossils were first found. Still, because they were discovered in pieces of rock that came from cliff faces, It's very likely that the pelvic girdles were close to the main armour, suggesting the fins were attached at the rear of the underside, just like in other armoured fish of the time. In at least one case, researchers may have even found the base of the pelvic fin right near the end of the trunk armour. Dunkleosteus torelli, one of the fiercest fish that ever lived, had an incredibly advanced jaw system. Scientists have discovered that it used a 4-bar linkage mechanism, a kind of natural machine made of 4 connected parts that could move together, just like the parts in a robot arm. These parts included the skull, a thick bony shield over the chest, called the thoracic shield, the lower jaw, and strong jaw muscles. All these pieces were connected with joints that allowed them to move smoothly and quickly. Thanks to this clever system, Dunkleosteus could open its jaws extremely fast in just 20 milliseconds, which is quicker than the blink of an eye. Even more impressive, the entire biting process, from opening to snapping shut, took only 50 to 60 milliseconds. That's about as fast as some of today's fish that use suction to suck prey into their mouths. But speed wasn't its only weapon. This ancient fish had incredible biting power. When scientists measured how strong its bite would have been, they estimated that it could deliver a force of about 4,440 newtons, roughly 992 pounds of force, at the very tip of its mouth. Even more powerful, the bite at the blade-like edges of its jaw could reach 5,363 newtons, and some estimates go even higher, up to 6,170 newtons at the tip and 7,495 newtons at the edge, which is more than 1,685 pounds of force. These numbers are not just impressive, they're record-breaking. Dunkleosteus had one of the strongest bites of any animal ever known, living or extinct. It was powerful enough to crack through the hard shells of armoured animals like ammonites and other placoderms, fish with thick bony plates for protection. Interestingly, fossil evidence has revealed even more about what this predator ate. Teeth from a type of cartilaginous fish called orodus, which swam fast in open water, were found near the remains of Dunkleosteus. Scientists believe these teeth were vomited up by the predator after a meal. Since Orodus was likely a fast swimmer, this suggests that Dunkleosteus was also much quicker than previously believed, able to chase down speedy prey, not just slow, bottom-dwelling creatures. Fossils of Dunkleosteus are often found with boluses, that is, lumps of fish bones that had been partially digested or chewed and then spat out. This tells us that it probably regurgitated the hard parts of its meals, such as bones, rather than digesting them fully. Just like some sharks and birds do today, it might have thrown up the parts it couldn't process. As they grew older, these ancient fish likely changed habitats. Juveniles, or young individuals, seem to live in shallow coastal waters, while fully grown adults probably moved into the deeper ocean, similar to the behaviour seen in some modern marine species. There's even evidence that Dunkleosteus may have fought with others of its kind. One fossil, catalogued as CMNH5302, shows puncture wounds, possibly caused by the bony fangs of another Dunkleosteus, hinting at aggressive behaviour or territorial battles. But perhaps the most fascinating discovery is that Dunkleosteus and its relatives might have been among the first vertebrates to fertilise eggs inside the body, much like how some sharks do today. In fact, a few placoderm fossils have shown signs of live birth, including one with what appeared to be an umbilical cord, a sign that the young developed inside the mother before being born. Studies of the lower jaws of young Dunkleosteus reveal something else surprising. Even as juveniles, they already had strong and thick jaws, not the thin and delicate ones you'd expect in young animals. This means they could bite into tough prey just like adults, though on a smaller scale. That's very different from what we see in animals like reptiles and mammals, where young ones usually have much weaker jaws. Opabinia regalis was a truly bizarre and fascinating creature that lived around 505 million years ago, during a time known as the Middle Cambrian period. It lived in the ancient oceans of what is now British Columbia, and its fossils were discovered in a famous fossil site called the Burgess Shale Lagerstätte. This animal is now extinct, and it belonged to an early evolutionary branch of the group that would eventually give rise to modern arthropods, such as insects, crabs, and spiders. Opabinia had a soft, squishy body, and could grow up to about 7 centimeters long from head to tail. Its body was divided into 15 segments, each with a pair of soft flaps sticking out from its sides. These flaps likely helped it swim slowly or move along the ocean floor. At the back of its body was a wide, fan-shaped tail made up of 3 pairs of overlapping blades that looked like 2 connected fans in the shape of a letter V. But the strangest and most attention-grabbing part of Opabinia was its head. It had 5 eyes, yes, 5, on stalks. 2 were near the front, pointing slightly forward and upward, 2 were farther back, pointing out to the sides, and 1 was located in the middle, peeking straight up. Just underneath the head there was a long, tube-like appendage known as a proboscis, which looked like a vacuum cleaner hose. It was flexible, striped with rings, and ended in a claw-like structure with 5 inward-facing spines. This proboscis was probably used to grab small, soft-bodied creatures or bits of food from the seafloor and bring them to the mouth. Even the mouth was oddly placed. It was hidden under the head, facing backwards. This meant that food had to be bent backward through the digestive system, which curled around inside the body. Scientists believe that Opabinia used its long, flexible proboscis to guide food into this backwards-facing mouth. Only fewer than 20 well-preserved Opabinia fossils have ever been found. In the most famous fossil layer of the Burgess Shale, called the Greater Philipod Bed, only 3 Opabinia specimens were discovered. They made up less than 0.1% of all the animals in that ancient ecosystem, meaning they were extremely rare. When paleontologists first studied Opabinia in detail in the 1970s, they were shocked by how strange it looked. At one scientific meeting where the animal's features were first shown to other researchers, the audience actually laughed out loud, not because it was a joke, but because they couldn't believe such a creature could have existed. At first, scientists didn't even know what kind of animal Opabinia was. Some thought it wasn't related to any known group of animals. Others guessed it might be a distant relative of both arthropods and segmented worms called annelids. But starting in the late 1990s, more studies and discoveries revealed that Opabinia was part of a group of early animals close to the base of the arthropod family tree. It is now often grouped with other strange Cambrian animals like Anomalocaris, a larger swimming predator, and lobopodian creatures like Kerygmacula and Pamdelurion, which had gill-like structures and leg-like appendages. The very first fossils of Opabinia were found in 1911 by the famous paleontologist Charles Doolittle Walcott, who discovered 9 almost complete specimens in the Burgess Shale. He also found a few fossils he called Opabinia media, but later researchers couldn't find these in his collection to confirm what they were. He published his descriptions in 1912 and named the animal after Opabin Pass, a scenic area between Mount Hungaby and Mount Biddle, southeast of Lake O'Hara in British Columbia. Another excellent fossil was found by Harry B. Whittington in 1966 or 67, and in 1975 he published a very detailed study of Opabinia, using carefully dissected fossils and creative lighting to better understand its shape and features. His study did not include Opabinia media, since those fossils were missing from the collections. In the 1960s, Russian paleontologists reported fossils from Siberia that they called Opabinia norilica, but the specimens were in poor condition. Whittington decided that they were too incomplete to be clearly identified as true Opabinia. All of the clearly recognised Opabinia fossils we know of today come from the Philipod bed of the Burgess Shale in the Canadian Rockies. In 1997, 2 researchers, Briggs and Needham, reported a fossil from South Australia's Emu Bay Shale called Megalodon, which was extremely well preserved. They suggested it might be closely related to Opabinia. However, another scientist, Jick, disagreed and instead believed that Megalodon was a type of segmented worm. The proboscis of Opabinia is particularly noteworthy. It was about 1/3 the length of its entire body and ended in a small claw. Some scientists believe this claw was actually formed from 2 separate appendages that had fused together, like the feeding limbs of other early arthropods. The animal's symmetry was bilateral, meaning its left and right sides were mirror images of each other. The body of Opabinia was only about 5 mm wide and had a soft outer surface. Because it didn't have a tough shell or armour, its body flattened when it was buried in mud and fossilised, making it hard to interpret some of the finer details. Different scientists over the decades have disagreed about the details of Opabinia's body, especially how its gills were arranged. Some thought they were thin, overlapping sheets attached near the top of each segment, while others believe they were individual blades attached in different places, either on the top, sides, or edges of the flaps. Another major debate focused on some mysterious triangular structures seen along Opabinia's body. Whittington thought they were internal parts of the gut, diverticular, or side branches that helped with digestion. But later, other scientists had different ideas. Budd, in 1996, thought they were actually fleshy legs, similar to the stubby limbs seen in Lobopodians. He even found tiny mineralized areas at the tips that he believed were claws. However, Zhang and Briggs, in 2007, tested the chemistry of these triangles and found that their makeup matched the gut, not external limbs. They concluded that the flaps with gill structures were the ancestors of what would later become arthropod limbs. The way the strange animals of the Burgess Shale were buried long ago gives scientists important clues about how they lived. These creatures, including Opabinia, were probably living right on top of the soft muddy seafloor. Then, one day around 505 million years ago, a sudden underwater mudslide, or a powerful current carrying loads of sediment like an underwater sandstorm, rushed in and buried them quickly. This sudden burial helped preserve even their soft bodies in great detail. Opabinia was one of the most bizarre and fascinating creatures from that ancient seabed. It had a long flexible tube sticking out from its head, like an elephant's trunk, which scientists call a proboscis. This strange appendage probably helped it search through the mud for tiny bits of food. The proboscis could likely pass these small particles directly into its backward-facing mouth. Since there's no sign of any kind of jaws or hard-chewing parts, it's very likely that Opabinia only ate soft and tiny things that didn't need much processing. Inside its body, Opabinia had paired sacs branching off the gut. These are called gut diverticula, which may have helped it digest its food more efficiently and absorb nutrients better. In the year 1975, a paleontologist named Harry Whittington studied Opabinia closely. He believed the animal didn't have legs at all. Instead, he thought it crawled along the ocean floor using soft flaps along its sides. These flaps may have also helped it swim slowly, possibly by moving in a wave-like rhythm known as metachronal motion, where each flap moved just after the one before it. However, Whittington also pointed out that Opabinia's body seemed too stiff to wiggle like a fish. Because Opabinia looked so strange and different from anything alive today, scientists spent much of the 20th century debating where exactly it fits on the tree of life. The first person to describe it was Charles Doolittle Walcott, who in the year 1912 thought Opabinia was a type of crustacean known as an anostracan, like today's fairy shrimp. Then, in the year 1930, G. Evelyn Hutchinson followed that idea and even made the first drawing of Opabinia as a shrimp-like creature swimming upside down. That view changed in the year 1970, when Alberto Simonetta proposed a completely different reconstruction. He suggested that Opabinia had many features similar to arthropods, such as a hard shell on its back and jointed limbs. His drawing reminded scientists of other Burgess Shale animals like Yohoia and Leonchoilia. Around the same time, Leif Sturmer believed that Opabinia was related to trilobites and similar ancient creatures. But after carefully analysing the fossils, Harry Whittington concluded in the year 1975 that Opabinia was not an arthropod at all. He couldn't find any sign of jointed limbs like those found in true arthropods. He also noted that its flexible tube-like proboscis was completely unlike anything seen in known arthropods. Whittington left the higher-level classification of Opabinia uncertain, but because of its unusual body, made up of ring-like segments but lacking joints, and its flaps with gills, he guessed that it might come from a very ancient group that eventually gave rise to both annelids, segmented worms, and arthropods, creatures with jointed legs and exoskeletons. Back then, many scientists still thought those two groups were closely related and grouped them together under the name Articulata. In the year 1985, Whittington and Derek Briggs published a detailed new description of another strange Burgess Shale creature called Anomalocaris. A year later, in 1986, Swedish scientist Jan Bergström noticed similarities between Anomalocaris and Opabinia. Both had flaps along their sides, blade-like gills, stalked eyes, and specialised front appendages. Bergström suggested that these creatures were primitive members of the arthropod family, although he believed arthropods weren't just one single group. In the year 1996, another scientist named Graham Budd made an important discovery. He believed he had found short, stubby, unjointed legs on Opabinia, something earlier researchers had missed. While studying a creature called Kerygmacula, found in Greenland's Sirius Posset fossils, and more than 10 million years older than the Burgess Shale, Budd noticed that it had very similar legs. He also saw strong similarities to another creature from the Burgess Shale named Achaia, and even to modern velvet worms called onychophorans, which are considered to hold many ancient features shared with early arthropods. By comparing all these creatures and their features, Budd built a sort of evolutionary family tree showing how modern arthropods may have evolved. Surprisingly, this tree even suggested that tardigrades, the tiny and hardy water bears we know today, might be the closest living relatives of Opabinia. However, not everyone agreed with Budd's ideas. In the mid-2000s, other researchers like Ho and his team proposed a very different view. They thought Opabinia belonged to a strange group of ancient worms called cycloneuralians, and that its arthropod-like features had developed separately by coincidence. In the year 2007, scientists Zhang and Briggs disagreed with Budd's interpretation that some triangular shapes on the fossil were legs. Still, they noticed that the way Opabinia's flaps and gills were arranged was very similar to the double-branched legs of arthropods, known as biramous limbs. Their analysis, like Budd's, placed Opabinia very close to the base of the arthropod family tree, though they didn't connect it to tardigrades. Even though scientists disagree about some of the finer details, most modern studies done since the 1980s have reached similar conclusions. They all recognise that Opabinia shares many important traits with early arthropods, like its segmented back, eyes on stalks, backward-facing mouth, and limb-like flaps with gills. These similarities are too strong to ignore. Since the early 2010s, most paleontologists no longer believe Opabinia is closely related to tardigrades or cycloneuralian worms. Instead, they now widely agree that Opabinia is a stem group arthropod, meaning it belongs to a very early branch of the arthropod evolutionary tree. It shares this position with other unusual animals like Anomalocaris and other members of a group called Radiodonta, as well as the gilled lobopodians. This conclusion has been backed up by many different evolutionary studies and new discoveries, such as evidence that Opabinia had gut glands similar to those found in true arthropods, and the discovery of a transitional fossil called Chylynxia. Then, in the year 2022, scientists described a new animal that looked quite a bit like Opabinia. It was found in rocks from Utah that date back to the Cambrian period. This fossil, named Eurypterid comosa, had actually been discovered earlier in the year 2008, but at the time it had been mistaken for a type of Anomalocaris. The discovery of Eurypterid suggests that Opabinia might not have been alone. There may have been several similar creatures in its family, meaning that this strange group of animals was more diverse and widespread than we once thought. The discovery of Opabinia was a real eye-opener. It showed just how little scientists truly knew about ancient animals that didn't have hard shells or bones, soft-bodied creatures that usually don't leave behind fossils. Because these animals decay quickly, their remains rarely survive the test of time, making fossils like Opabinia incredibly rare and valuable. When the paleontologist Harry Whittington carefully described Opabinia in the middle of the 1970s, experts were already locked in a passionate debate about how early animals evolved. Back in the years 1948 and again in 1968, geologist Preston Cloud had proposed that the evolution of complex life had happened in a sudden burst. He called it an explosive event, suggesting that life didn't develop slowly and steadily, but instead leapt forward in a dramatic surge. Then, in the early 1970s, two paleontologists named Niles Eldridge and Stephen Jay Gould introduced a new idea called punctuated equilibrium. According to this theory, evolution usually moves at a snail's pace, staying almost unchanged for long periods of time. But every now and then, something triggers a quick burst of changes, a short, rapid leap in evolution that creates many new forms of life. Not everyone agreed with this view. Around the same time, scientists like Wyatt Durham and Martin Gleisner believed that animals had actually been evolving slowly for a very long time, stretching all the way back through the Proterozoic eon, which began over 2 billion years ago. They thought the reason we don't see their fossils is because soft-bodied creatures simply didn't fossilize well, not because they didn't exist. In the year 1975, Harry Whittington reached a fascinating conclusion. After studying Opabinia and other unusual animals like Morella and Yohoia, he realized that these creatures didn't fit into any of the animal groups we know today. They were too different. This idea, that many early Cambrian animals belonged to no modern groups at all, was so striking that it inspired Stephen Jay Gould to write an entire book about it. The book was called Wonderful Life, and in it, Gould argued that life during the Cambrian period was far more diverse and experimental than anything that came afterward. He believed that the Cambrian explosion, which happened more than 500 million years ago, was a truly extraordinary moment in the history of life, maybe even powered by unique evolutionary forces we don't fully understand. Gould was so amazed by Opabinia that he even considered naming the book homage to Opabinia. Soon, more fossils were discovered that added to the story. Scientists found other animals that looked just as strange. One of them was Anomalocaris, also from the Burgess Shale, and another was Keragmacula, discovered in the Sirius Passet fossil site in Greenland. These bizarre animals helped researchers understand that Opabinia wasn't alone. It was part of a larger picture of weird, early life. Another creature, Achaia, was found in the Burgess Shale too, and it looks surprisingly similar to today's velvet worms or Onychophora. These modern worms are soft-bodied and have stubby legs, and scientists now consider them close cousins of arthropods, the group that includes insects, spiders and crabs. To help make sense of these odd creatures, scientists created a group called Lobopodians. This group includes ancient animals that are closely related to today's arthropods, velvet worms, and even the tiny, water-loving tardigrades. Lobopodians didn't have jointed legs like modern arthropods, but they may represent the early stages of how these animal groups first evolved. Scientists now think of Lobopodians as a paraphyletic grade, which means they were part of an evolutionary stepping stone that led to modern groups, but weren't themselves part of the final picture. As these debates unfolded in the second half of the 20th century, researchers began to use a new way of thinking about evolution. They introduced the concepts of crown groups and stem groups. A crown group includes all living members of a group, their last common ancestor, and all of its descendants. For example, all modern insects, spiders and crustaceans belong to the arthropod crown group. A stem group, on the other hand, includes earlier relatives, those aunts and cousins of modern animals that branched off before the crown group formed. It's a flexible way of organising the tree of life. To make things more interesting, in the year 1996, researcher Graham Budd suggested that even living animals like tardigrades could be seen as a stem group in relation to arthropods. That might sound confusing at first, but it simply means they branched off early and hold important clues to how arthropods evolved. When strange creatures like Opabinia are seen through this lens, the mysterious Cambrian explosion doesn't seem quite so magical. Instead, it becomes something we can understand as part of evolution's normal, but still awe-inspiring process. Cladoselache was an ancient type of fish that looked very much like a modern shark, though it lived long before true sharks evolved. This remarkable creature swam through the oceans during the late Devonian period, around 375 million years ago in what is now North America. At first glance, Cladoselache had a body shape that might remind us of modern fast-swimming sharks, like the great white shark or the sleek mako. However, it was not closely related to these modern sharks or any of today's shark groups. Cladoselache belonged to an early group of cartilaginous fish known as chondrichthyans, animals with skeletons made of cartilage rather than bone. Because Cladoselache lived so long ago, it still lacked several features that modern sharks have today. For example, it did not have the ability to quickly replace lost teeth, its jaws were not loosely hinged like those of present-day sharks, and its teeth did not have the hard, shiny enamel coating called enameloid. It's also possible that Cladoselache did not yet have claspers, the special organs that male sharks use during mating. During the 20th century, many scientists believed that Cladoselache belonged to a very early branch of the group called Elasmobranchi, which eventually led to modern sharks and rays. But more recent and detailed studies have taken a fresh look at its skull, fin spines, and the base of its pectoral fins. These features suggest that Cladoselache was more closely related to an odd little group of ancient cartilaginous fish known as Cimmeriiforms, a group that includes the strange, spiky-headed Stethocanthus. In fact, Cladoselache and the Cimmeriiforms might not have been close relatives of true sharks at all. Instead, they might have been more closely related to another group of weird-looking sea creatures that still exist today, the deep-sea fish called chimeras, sometimes known as ghost sharks or ratfish. Cladoselache could grow to be several meters long, with the largest confirmed specimen measuring about 2 meters or 6.5 feet from head to tail. Its long, narrow body and deeply forked tail made it an excellent swimmer. It was likely a fast, agile predator that chased down its prey in open waters. Cladoselache is one of the most well-understood early cartilaginous fish, thanks to the incredible fossils discovered in the Cleveland Shale, a rock formation found near the southern edge of Lake Erie. These fossils are more than just bones, or rather cartilage. Some are so well preserved that they even show soft tissues, like muscles, skin, and internal organs such as the kidneys. That kind of preservation is extremely rare in fossils this old. The skeleton of Cladoselache was made of a special type of cartilage known as tessellated cartilage. This material is unique to cartilaginous fish. It's made of flexible cartilage fibres, but strengthened with a loose puzzle-like pattern of small calcified plates called tesserae. This combination made Cladoselache's body both strong and flexible, ideal for a fast-moving predator. The head of Cladoselache had a shape that was somewhat similar to today's frilled sharks, while its body shape resembled that of mackerel sharks, such as the great white or mako. These modern comparisons suggest that Cladoselache might have lived and hunted in similar ways. Just like other cartilaginous fish, Cladoselache had a skull made of cartilage, called a chondrocranium, that protected its brain and sense organs. It had 2 jaw cartilages, one upper, the palatal quadrate, and one lower, called Meckel's cartilage, both lined with teeth. Its eyes and nasal capsules were large and set forward on its face, which probably gave it good vision and sense of smell, useful tools for a hunter. Although its gill basket is not well understood, the available evidence suggests it had at least 5 pairs of thin, widely spaced gill arches, meaning it most likely had 5 gill slits on each side of its head. Some early studies suggested that it might have had 6 or even 7, but that has not been proven. Between each gill slit were muscular flaps lined with delicate, overlapping filaments that helped it breathe underwater. Cladoselache also had a pair of large pectoral fins just behind the gills and smaller pelvic fins farther back. Along its back were 2 dorsal fins. The first dorsal fin was larger and had a strong curved spine in front of it, likely for protection or support. The tail was long, narrow and strengthened with ridges, ending in a crescent-shaped caudal fin that gave the animal powerful thrust. The brain case, or chondrocranium, was low and flat, with different regions serving various purposes. The part above and between the eyes, called the sphenoid region, was wide and triangular. Behind that was the otic region, which covered parts of the brain and organs that controlled balance. The front part of the brain case, near the nostrils, the ethmoid region, is not fully known from fossils, but it was probably short and did not extend into a long snout like in today's sharks. On the underside of the brain case were openings for nerves and blood vessels. At the very back was a deep hollow, connected to the spinal column. Inside this hollow were 2 closely placed openings where the dorsal aorta, a major artery, entered the skull to supply blood to the brain. This arrangement shows that Cladoselache had a blood vessel layout that was somewhere between that of Cimmeriiforms, with just one such opening, and other early cartilaginous fish, with more widely spaced openings. Many other details in the brain case also link Cladoselache with the Cimmeriiforms. For example, the openings for the orbital arteries, which bring blood to the eyes, were located just in front of the arteries that entered the brain. A part of the skull called the postorbital process, which separates the eye from the ear region, was stretched from side to side and narrowed in the middle. The supraorbital shelf, a wide plate above the eyes, had a notch on its edge. However, there were also important differences. In Cladoselache, all the exits for the branches of the facial nerve, nerve number 7, were located far away from the eye arteries. In contrast, in the Cimmeriiforms, some branches of this nerve were bundled with the eye arteries and passed through a shared groove or opening. The skeleton of Cladoselache, an ancient shark-like fish, was quite different from modern sharks. Its upper jawbone, called the palatoquadrete, and lower jawbone, called Meckel's cartilage, were relatively thin and lightweight. Inside these jaws, rows of sharp teeth grew side by side, sitting in scalloped or wavy grooves that stretched across the mouth. Its mouth was located right at the front of its head, a feature also seen in the modern frilled shark, Chlamydocelicus, which makes it different from most sharks living today, whose mouths are usually underneath their heads. The connection between the upper and lower jaws was not very strong, but on the outer surface of the jaws, scientists have found spots where large, sheet-like muscles probably attached, allowing for powerful bites. At the back end of the upper jaw, a part called the otic process curved upward and connected with a part of the skull known as the postorbital process. The front part of the upper jaw also curved outward slightly and likely attached to the ethmoid region of the skull. This two-part connection between the jaw and skull is something also seen in ancient sharks called xenacanthids. The back edge of the upper jaw was supported by a rod-like bone called the hyomandibula. Since Cladoselache's jaw was connected both to the skull and the hyomandibula, scientists say that it had a type of jaw structure called amphistole. This kind of structure was common among the earliest cartilaginous fish, but today it only exists in certain deep-sea sharks like frilled sharks and six-gill sharks. In contrast, most modern sharks and rays have a different kind of jaw connection called hyostole, where the jaw is only held by the hyomandibula. On the other hand, chimeras have jaws that are completely fused to the skull, a condition called holostyle. Cladoselache also had a special kind of tooth called a cladodont tooth. Each tooth had a large, sharp point in the middle, called the central cusp, with one or two smaller points on either side called lateral cusps. The side of the central cusp that faced the cheek, the labial face, was flat, which is different from many other cladodonts that had a rounded or bulging cheek side. The root of each tooth was broad and deeply curved underneath, forming what's called a basiolabial depression. Triangular extensions stuck out from either side of this depression. The teeth at the front of the mouth were taller and more dramatic, with one long central point and two pairs of smaller points. Interestingly, the outer pair of smaller points were larger than the inner pair. Farther back in the mouth, the central point on each tooth became shorter, and the inner pair of smaller cusps disappeared completely, leaving only the outer pair. These teeth were made of thick layers of dentine, a hard tissue, but they lacked enamel, which is the hard outer layer found in bony fish teeth, or enameloid, a similar tissue found in modern shark teeth. Cladoselache was one of the first known vertebrates to show a shark-like system of tooth replacement. New teeth grew outwards in rows from deeper inside the jaw, pushing older teeth towards the edge of the mouth. Each tooth row contained around 7 to 9 teeth that were closely packed together, and there were about 11 or 12 rows arranged one behind the other on each side of the upper jaw. Interestingly, the oldest teeth at the outer edge of each row were smaller than the newer teeth further in, which suggests that tooth replacement happened slowly enough to keep up with the animal's overall growth. This is supported by the fact that many teeth show signs of wear, meaning they were kept and used for a long time before being replaced. The spine of Cladoselache was made of cartilage and not bone, so it didn't preserve well in fossils. It did not have calcified centra, which are the spool-shaped segments that make up the backbones of many other vertebrates. Usually, only the neural arches, sharp, bony projections that sat on top of the spinal cord, can be seen in fossils. All of Cladoselache's fins, except for the tail fin, followed the same general design. Each had a wide base that blended into the body in a triangular shape. These fins were supported by stiff cartilage rods called radials that extended nearly the entire length of the fin. Only a few of the radials were divided into sections. The thicker ones were found at the front of the fin, while thinner ones were placed towards the back. The pectoral fins, the ones just behind the head, were long and strong. They connected to a broad and sturdy pectoral girdle which supported them. From the base of each pectoral fin, a tall bone called the scapula projected upwards. Deep inside this girdle were a pair of L-shaped bones called procoricoids, which are also found in many other ancient sharks. Each procoricoid connected to a large wing-like coracoid plate that formed the base of the fin. The front half of each pectoral fin had 11 radials, the first 6 of which were long and undivided. The next 5 were split into 2 segments, a short inner part called proximal radials, and a longer outer part called distal radials. The back half of the pectoral fin included a triangular cartilage structure called the metapterygium, which stretched out from the rear of the coracoid plate. More than 6 slender radials connected to the metapterygium. Many of these traits, large paired procoracoids, segmented radials, and a well-developed metapterygium, are also seen in a group of ancient sharks called cimariiforms. However, Cladoselache had a special feature not seen in most of its Paleozoic relatives. The back edge of its metapterygium did not send out a row of small cartilage bits called axials. The pelvic fins, located near the rear of the body, were small and low, measuring about 3 times longer from front to back than they were tall. Their cartilage supports, or radials, sloped backward and connected to a set of small linking bones called basals, which were buried inside the body. Basals also help support the dorsal fins, the fins on the back. A pair of pointed, rod-shaped structures may represent a primitive form of pelvic girdle sticking forward from each set of basals. Interestingly, no claspers, the male reproductive structures seen in most sharks, have ever been found in Cladoselache fossils. This could mean that the species used external fertilization, or that we simply haven't found enough male fossils to confirm it. Cladoselache did not appear to have an anal fin. However, under the narrow part of the tail, scientists found 6 pairs of cartilage structures that swept forward. These may be the evolutionary relatives of the missing anal fin. The first pair of these structures was especially large, and they extended all the way to the base of the tail fin. The tail fin itself was one of Cladoselache's most unique features. It had a tall, crescent moon-like shape, rising sharply from a narrow base. This kind of lunette tail is also seen in fast-swimming fish like the modern swordfish, Cepheus. The notochord, the flexible rod running along the back, bent sharply upward and extended all the way to the tip of the upper lobe of the tail. The upper lobe was made up of stacked cartilage plates called epurals. The largest epurals were at the top front, forming a pointed edge. The lower lobe of the tail was strengthened by at least 12 thick radials. It's unclear whether these attached directly to the notochord or were connected through basals. The back edge of the fin was made of flexible dermal fibres, rather than rigid bone. On both sides of the narrow tail stalk, wide flaps called keels helped stabilise the tail, making it look almost rectangular from above. Cladoselache had 2 dorsal fins. The first dorsal fin sat above the pectoral fins and was much taller than the second dorsal fin, which was located above the pelvic fins. At first, scientists thought Cladoselache didn't have fin spines, which are common in many ancient sharks. But in the year 1938, fossils were discovered showing a stout spine-like structure in front of the first dorsal fin. This spine was slightly curved backward and was almost as long as it was tall, very different from the thin, needle-like spines seen in other prehistoric sharks. The spine had no decorations except for some random grooves across its surface. It was probably only shallowly embedded in the skin and didn't closely connect to the rest of the dorsal fin. Inside, the spine was made of calcified cartilage covered in layers of cellular and acellular dentine, a bony tissue. This internal makeup is most similar to the spine brush complex seen in cimariiforms, and not to the enamel-covered spines of other sharks. While a related species called Magrobosolache had spines in front of both dorsal fins, we're still not sure if Cladoselache had a spine in front of its second dorsal fin. Some scientists think it probably did, others think it did not, and many remain uncertain. Cladoselache is considered one of the best-known early members of a group of fish called the chondrichthyans. These are animals with skeletons made of cartilage instead of bone. Today that group includes sharks, rays and deep-sea creatures called chimeras, which are also known as ratfish or ghost sharks. Even though Cladoselache looked very much like a modern shark and probably lived in a similar way, it was not a true shark by today's scientific definitions. In fact, the kinds of sharks we're familiar with today, known as Selachians, did not appear until millions of years later, during the Jurassic period, which began around 201 million years ago. When scientists first described Cladoselache in the late 19th century, they quickly realised it was a very ancient type of cartilaginous fish. Even though it had a shark-like body, it was actually a much more primitive or ancestral form, only distantly related to modern sharks. That's why Cladoselache is often called the earliest shark, although in reality, It's more accurate to think of it as one of the earliest chondrichthyans, part of the broad, early group from which sharks, rays and chimeras all evolved. Interestingly, the general shark-like body shape of Cladoselache is believed to be the original or ancestral shape for the entire chondrichthyan group. This means even rays and chimeras, which look very different today, likely evolved from ancestors that had a body somewhat like a shark. Early in the history of cartilaginous fish, this group split into two major branches. One branch is called Holocephali, or Euchondrocephali, which was once much more diverse during the ancient Paleozoic era, but today is only represented by the rare and strange chimeras. The other branch is known as Elasmobranchi, which includes all modern-day sharks and rays, as well as many of their extinct relatives. In the past, some scientists used terms like shark, elasmobranch, and chondrichthyon, as if they meant the same thing. However, modern research has shown that these labels actually refer to different branches within the same larger group. In the earlier studies of Cladoselache, scientists thought that it, along with another group of ancient fish called acanthodians, sometimes called spiny sharks, belonged to the base of the elasmobranch group. However, both groups had some strange and unique features that didn't quite match the expected primitive characteristics. These two groups were once placed together in an outdated classification called Pleuropteridae, because they shared features like ring-shaped eye bones called scleral rings, flap-like fins, a reinforced upper tail lobe, and the apparent absence of claspers, reproductive organs found in male sharks. Later, this group Pleuropteridae was expanded to include other ancient shark-like animals such as tenacanthids and cimeriids, which were similar in age and structure to Cladoselache. They all shared certain traits like cladodont teeth, which have a central point and smaller side points, and other features in their body structure. Fossils eventually revealed that Cladoselache did have dorsal spines, which added support to the idea that it and other groups like the tenacanths and hybodonts represented a gradual series of forms that became more and more advanced, eventually leading to the sharks we know today. Throughout the 20th century, scientists mostly agreed that Cladoselache was one of the earliest known members of the cartilaginous fish group. The main disagreements were about exactly how early it branched off from the family tree. Some studies placed it at the very base of the chondrichthyan group. Others thought it might have been an early elasmobranch, possibly appearing a little after the holocephalans, the chimera ancestors. A few researchers even suggested Cladoselache was more closely related to later sharks and rays, particularly the hybodonts and neoselachians, the group that includes all living sharks and rays. But that idea was never very stable. In the 1980s, scientists noticed that the shape of Cladoselache's tail was similar to that of a mysterious group of ancient fish called Eugeniodonts, though the connection remained uncertain. More recent studies of Cladoselache's anatomy, especially its brain case and pectoral region, the area near the front fins, suggest that it may be closely related to the Cimeriiforms, a group of ancient cartilaginous fish that includes creatures like Stethocanthus and Falcatus. Cladoselache's dorsal spine may be similar in origin to the unusual head structures found in Cimeriiforms. Some researchers now believe that Cladoselache and the Cimeriiforms may belong to a very early offshoot of chondrichthyans, possibly at the base of either the elasmobranch or chondrichthyon lineage. However, a new theory has gained popularity. According to this idea, Cladoselache and the Cimeriiforms might actually lie on the opposite side of the chondrichthyon family tree as early relatives of holocephalans, the branch that would eventually give rise to today's chimeras. This theory was first based on features like their lack of body scales, missing second dorsal spine, and later supported by details in the brain structure, such as a curved midbrain and large eye sockets. The teeth of Cladoselache were long, smooth and thin, ideal for grabbing prey, but not for ripping or chewing. Fossils found in the Cleveland Shale, a rock formation in what is now the United States, show remarkable preservation. In fact, some Cladoselache fossils still had stomach contents inside them, giving us a clear view of what they ate. These meals mostly included small bony fish, like Kentuckia halevini, although this fish might not actually belong to that genus, as well as strange shrimp-like animals called thylacoscephalans and conodonts, which were soft-bodied, eel-like creatures with primitive teeth. Some of the fish remains were found tail first inside the stomachs, which tells us something fascinating. Cladoselache likely swallowed its prey while chasing it, showing that it was a quick and skillful hunter. One mystery still puzzles scientists. How did Cladoselache reproduce? Unlike most other early sharks, Cladoselache did not have claspers, the male organs used to transfer sperm during mating. This is unusual, and no one is yet sure how Cladoselache reproduced. It might have used internal fertilization, like modern sharks, but there's no direct evidence of this yet. Cladoselache had tiny tooth-like scales, known as placoid denticles, but these were short and cone-shaped, and were not found across the entire body. Larger denticles appeared on the edges of the fins and along the lateral line, a sensory organ used to detect movement in water. Some areas near the jaw had three-pointed denticles. These denticles had an internal structure made of fused dentines surrounding small pulp-filled cavities. Its eyes were surrounded by a ring of more than 20 small bone-like plates, which were originally thought to be just more denticles. Later studies showed they were true scleral ossicles, tiny bones like those seen in the eyes of modern bony fish and early tetrapods. Modern sharks, by contrast, only have a cup-shaped ring of hardened cartilage instead of true scleral rings. The Cleveland shale also preserved many soft tissues of Cladoselache that usually rot away before fossilization. Inside its body, scientists found a pair of long, tube-filled organs located between the pelvic fins and the tail. These may have been kidneys, although their location is quite unusual. This suggests that Cladoselache's internal organs, including its digestive and urinary systems, extended farther back into the tail region than they do in modern sharks. The digestive system seemed to twist in a way that's similar to that of living sharks, and fossilized waste, coprolites, showed the same kind of spiral structure. The muscles of Cladoselache were divided into clear bundles, making it easier for researchers to study its muscular system than in most modern sharks. Eurypterids, which are often called sea scorpions, were an ancient group of water-dwelling arthropods, creatures with hard exoskeletons, jointed legs and segmented bodies. Even though they looked somewhat like scorpions, they were not true scorpions, and the nickname is mostly based on their appearance. They belong to a now extinct group known as the order Eurypterida. The oldest known Eurypterid fossils date back to the Darwinian stage of the Ordovician period, which began around 467 million years ago. However, scientists believe these animals may have first evolved even earlier, perhaps during the early Ordovician, or possibly near the end of the Cambrian period. With nearly 250 known species, the Eurypterids represent the most diverse group of Paleozoic chelicerates, a larger class of arthropods that also includes spiders, scorpions, and horseshoe crabs. After they first appeared, Eurypterids became especially successful during the Silurian period, which followed the Ordovician. Most species of Eurypterids described by scientists today come from rocks of this time. The Silurian period also saw an important evolutionary event. Arachnids, the group that includes modern spiders and scorpions, split from their water-dwelling relatives and began adapting to life on land. One genus of Eurypterids, known as Eurypterus, was so common during the Silurian that it makes up more than 90% of all Eurypterid fossils ever found. Although Eurypterids continued to evolve and diversify into new forms during the Devonian period, a major extinction event near the end of that era, the late Devonian extinction, caused their numbers and variety to decline sharply. Eventually, all remaining Eurypterids disappeared completely around the time of the Permian-Triassic extinction event, which happened approximately 252 million years ago, or possibly a little earlier. Despite their nickname, sea scorpions, only the earliest Eurypterids lived in the ocean. As time passed, many species adapted to life in brackish, slightly salty, or even fresh water. Some scientists believe that they might have even been able to survive briefly on land. There is evidence suggesting that Eurypterids may have had a type of dual respiratory system, one part for breathing in water and another possibly for breathing air for short periods, like modern crabs or amphibians. The name Eurypterida comes from two words in ancient Greek, eurus, meaning broad or wide, and pteron, meaning wing. This name refers to the wide, paddle-like limbs that many of these creatures used to swim through the water. Eurypterids are especially famous because they include the largest arthropods, that is, the largest joint-legged animals, to have ever lived. The biggest of them all, called Echolopterus, may have grown up to 2.5 meters long, which is about 8 feet and 2 inches. That's bigger than most humans. However, not all Eurypterids were giants. Most of them were actually quite small, less than 20 centimeters, or about 8 inches in length. The smallest species ever discovered, Alcanopterus, was only about 2 centimeters long, less than 1 inch. Fossils of Eurypterids have been found on every continent, but the majority come from fossil beds in North America and Europe. This is because most Eurypterids lived in the ancient seas and coastal waters that surrounded Euramerica, a prehistoric supercontinent that existed hundreds of millions of years ago. Only a few groups of Eurypterids managed to spread outside of this area, but some, like Adelophthalmus and Pterygotus, became so widespread that their fossils are now found all around the world. Like all arthropods, Eurypterids had segmented bodies, jointed limbs, and a tough outer covering made of protein and chitin. Their bodies were divided into 2 main parts. The front part, called the prosoma, is similar to a head, while the back part, known as the opisthosoma, is like an abdomen. The prosoma was protected by a hard shell known as the carapace, which had both compound eyes, like those of insects, and ocelli, simple eye-like structures that could detect light. Attached to the prosoma were 6 pairs of limbs, labelled from pair 1 to pair 6. The first pair, known as the chelicerae, was located just in front of the mouth and was used to grab and handle food. These limbs ended in small pincers. In one family, the Pterygotidae, these pincers became much larger and had sharp, tooth-like structures for catching and cutting prey. The next 5 pairs of limbs, pairs 2 through 6, were mainly used for walking, though they also had special structures on their base segments, called gnathobases or tooth plates, to help with feeding. These legs were usually round in shape and often covered with spines. In many species, the limbs grew larger toward the back of the body. In a subgroup of Eurypterids called the Eurypterina, the 6th pair of limbs was flattened into broad paddles, which helped them swim. The back portion of the body, the opisthosoma, had 12 segments, ending in a structure called the telson. In most species, the telson looked like a flat, blade-shaped tail. In some lineages, such as the Pterygotioidea, Hibbertopteridae, and Micteroptidae, this telson was even flattened further and may have worked like a rudder to help steer while swimming. In a few types, like Eusarcana, the telson looked like a scorpion's tail and might have been used to deliver venom, much like a real stinger. Beneath the body, the underside of the opisthosoma was covered in leaf-like plates called Blattfusa, which is German for leaf feet. These formed a chamber for the gills, helping the creature breathe underwater. In some parts of the abdomen, scientists have found oval or triangle-shaped structures, known as gill tracts, that may have helped the animal breathe air when out of water for short periods. These were similar in function to the structures found in today's horseshoe crabs. 2 of the Eurypterid's body segments, the 7th and 8th, had special limbs that were fused together to form a structure called the genital operculum, which covered the reproductive organs. At the front edge of this structure was a special appendage called the zipful, or median abdominal appendage. This part is often very well preserved in fossils and is thought to have been part of the reproductive system. Fossils show 2 distinct versions of this organ, likely representing male and female individuals. Eurypterids were a group of ancient marine animals that came in many shapes and sizes. These extinct creatures belong to a group called arthropods, which includes insects, spiders, and crabs today. Depending on how they lived, where they lived, and what kind of Eurypterid they were, their body size could vary a lot. For many Eurypterid species, a length of around 100 centimeters was quite normal, but some were much smaller and others grew to absolutely enormous sizes. The smallest known Eurypterid ever found is called Alcanopterus burglarhensis. It was tiny, just a little over 2 centimeters long, or about 0.8 of an inch. On the other end of the scale, the largest Eurypterid, and in fact the largest known arthropod, joint-legged animal, to ever exist, was a terrifying predator called Echolopterus rhenaniae. Fossils of this giant were discovered in the ancient rocks of Wilverath, Germany, in what is called the Emsian Klurf Formation. One of its front claws, called a chelicera, was found to be 36.4 centimeters long, even though part of it was missing. Experts believe the full claw was likely 45.5 centimeters long. By comparing it with the claws and body sizes of its closest relatives, Scientists estimate that this particular Echilopterus could have been between 233 centimeters and 259 centimeters in length. That's between 7 feet and 8 inches and 8 feet and 6 inches long. On average, it likely measured around 2.5 meters, or 8 feet and 2 inches, not even counting its claws. If the claws were stretched out in front, it would have reached about 3.5 meters. That's over 11 feet! Even without counting its outstretched claws, Echilopterus was nearly 0.5 meter longer than any other known giant arthropod. 2 other Eurypterids may have reached similar sizes. One was Eratopterus grandis, a close relative of Echilopterus, but only fragments of this species have been found. The other was Hibbertopterus witterbergensis, whose large size is guessed based on fossilized trackways, fossil footprints, not from actual bones or exoskeletons. Echilopterus belonged to a family of sea scorpions called the Pterygatidae, which was famous for its giant members. Another member of this group was Acuteramus, whose largest species, Acuteramus bohemicus, is thought to have grown up to 2.1 meters long, or almost 7 feet. Then there was Pterygotus, with its largest species, Pterygotus grandidentatus, reaching about 1.75 meters. These sea scorpions were true giants of their time. Scientists believe several reasons may explain why the pterygatids became so big. These reasons include mating behavior, hunting needs, and competition for food and territory. But the Pterygatidae family wasn't the only group with giants. Another sea scorpion, Carcinosoma punctatum, which belonged to a different family called the carcinosomatoids, is known from a fossilized body part called a metastoma that was 12.7 centimeters long. That single part suggests the whole animal may have been about 2.2 meters long, making it as big as the giants in the Pterygatidae family. Yet another massive Eurypterid was Pentacopterus decrahensis, an early carcinosomatoid, which may have grown up to 1.7 meters long. Most of these giant sea scorpions had something in common. They were built light. Their bodies weren't bulky or heavy, which helped them move easily in the water, molt their exoskeletons without too much effort, and breathe more efficiently. Their outer shell was often thin and not strengthened with minerals, making them less dense than you might expect. This lightweight body design is not only seen in sea scorpions, but also in other prehistoric giants like Arthropleura, a massive millipede. It's likely that this adaptation was very important for arthropods to evolve to such large sizes. However, not all big Eurypterids were lightweight. Some, like those in the Hibbertopteridae family, were broad and heavy-bodied. One fossil of a wide carapace, the upper shell from Scotland, which belonged to Hibbertopterus sculeri, measured about 65 centimeters across. Since this creature was much wider than it was long, it might have been nearly 2 meters long. Because of its bulky body, this Hibbertopterus may have weighed as much, or even more, than the longer but slimmer pterygotids. There were 2 major groups of Eurypterids, Eurypterina and Styloneurina. They looked similar in many ways, but the main difference was in their last pair of limbs. In Styloneurina, the final legs were long and skinny, and likely used for walking. In Eurypterina, however, the final legs were flattened into broad paddles, perfect for swimming. While most of the Eurypterines had small legs suited for crawling along the seafloor, many Styloneurines had strong legs that might have even let them walk on land, similar to how modern crabs sometimes do. A truly remarkable fossil discovery was made in Scotland in the year 2005. Scientists found a fossilized trackway, a trail left by an animal as it walked, that matched a Eurypterid about 1.6 meters long. The footprints were wide, averaging 95 centimeters, and the trackway stretched out for 6 meters, or almost 20 feet. It is the largest known trail ever made by an arthropod on land, and provides solid proof that some Eurypterids could survive on land, at least for short periods. The trail belonged to Hibbertopterus, which had different-sized limbs, a condition called heteropodous limbs. The fossilized track suggests that it moved very slowly and unevenly, dragging its tail behind and leaving a deep groove in the mud. Smaller Eurypterids like Parastyloneurus probably moved more quickly and with more precision. When it came to swimming, not all Eurypterids were equally good at it. In some groups like Eurypteroidea, their paddle-shaped legs moved like oars, but only in flat horizontal motions. Other groups, such as Pterygotoidea, may have had more flexible paddles, making them faster swimmers. Most swimming Eurypterids used a rowing motion similar to how crabs and water beetles move today. Some of the larger ones might have even used subaqueous flight, gliding through the water much like sea turtles or sea lions. This kind of swimming is slower to start but more energy efficient, especially for large creatures with smaller paddles compared to their body size. Not all sea scorpions were graceful swimmers though. For example, Mixopterus, as shown by its fossilized trackways, probably stayed near the sea floor. It may have used short swimming bursts and mainly crawled along the bottom. While walking, it used a motion similar to modern insects. Its long, heavy abdomen was balanced by large front limbs, and it may have adjusted its balance using its tail. Fossilized trackways from Eurypterids are found all over the world, on every continent except South America. In some places like South Africa, where body fossils are rare, tracks are more common and often appear before any body parts are discovered. These tracks are often labelled with scientific names like palmicnium, which usually shows a series of 4 footprints and a central tail drag mark. One of these tracks, called Palmicnium cosinciorum, contains the largest known sea scorpion footprints, each about 7.5 centimeters wide. As for how these animals breathed, they had special respiratory structures underneath their bodies, inside what's known as a gill chamber. These gill tracts were often spongy and covered with tiny spines to increase surface area. However, many scientists believe these organs were not true gills like those found in fish or other aquatic animals. Instead, they might have been more like pseudotraei, structures similar to lungs that are found in some modern isopods, a type of crustacean. This suggests that Eurypterids may have had a unique way of breathing, possibly allowing them to survive briefly on land, but they were still primarily aquatic animals. Eurypterids, like all arthropods, grew by molting their exoskeletons in stages called instars. After each molt they grew quickly. Unlike insects, they probably didn't go through drastic changes during their life. They were what scientists call direct developers, meaning they looked similar to adults even when they first hatched. Some earlier theories had suggested otherwise, but fossil evidence, especially from sites in Wyoming, where well-preserved young and adult Eurypterids were found together, shows that Eurypterids likely hatched with all their body parts already present. As they grew older, one part of their body called the metastoma, a plate-like structure under the body, usually became narrower in proportion to their size. This pattern has been seen in many Eurypterid groups. Even though no fossilized stomach contents have ever been found, the body structure of Eurypterids suggests they were meat-eaters. They had good depth vision, spiny legs for grabbing prey, and some even had sharp claws. Some types, like Mixopterus and Megalograptus, had long spiny arms for capturing food. Others, like Pterygotioidea, had claws instead of spines. Some Eurypterids probably fed like modern horseshoe crabs, using their limbs to tear food apart and pass it to their mouths with their front claws. Interestingly, fossilized poop, called coprolites, from some ancient Eurypterids contains fragments of other Eurypterids and trilobites. One species, Lanacopterus, even shows evidence that it may have eaten members of its own kind, a case of cannibalism. While only the biggest sea scorpions may have ruled their seas as apex predators, even the smaller ones were likely fearsome hunters in their own right. Mosasaurus, which means lizard of the Meuse River, was a truly remarkable sea creature that ruled the oceans during the last part of the age of dinosaurs. It belonged to a group of ancient water-dwelling reptiles called mosasaurs, which were close relatives of today's lizards and snakes. These powerful marine predators lived roughly between 82 and 66 million years ago, during the Campanian and Maastrichtian stages of the late Cretaceous period. This genus, Mosasaurus, is considered the most important or type example of all mosasaurs. It was one of the very first large marine reptiles from the Mesozoic era to be discovered and studied by scientists. The first fossils were uncovered in the late 1700s in a chalk quarry near the city of Maastricht in the Netherlands. At that time, the idea of extinction was still new, and people had trouble believing that any species could disappear forever. When they first found the giant skulls of Mosasaurus, some thought they belonged to crocodiles, while others believed they came from enormous whales. One particularly large and mysterious skull, found around the year 1780, became famous and was nicknamed the Great Animal of Maastricht. Then, in the year 1808, a French scientist named Georges Cuvier examined the bones more closely. He concluded that the skull came from a huge marine lizard, something that looked a bit like a monitor lizard, but unlike anything alive today. This was a groundbreaking idea at the time. Cuvier's research helped support the then new concept that some animals, like dinosaurs and giant sea reptiles, had once lived but had vanished forever. Even though Cuvier gave this animal scientific attention, he did not give it an official name. That task was taken up in the year 1822 by a British naturalist named William Daniel Conybeare. He named the animal Mosasaurus after the Meuse River, called Mosa in Latin, which flowed near where the fossils were found. Later, in the year 1829, another scientist named Gideon Mantell added the species name Hoffmanni to honour Johann Leonard Hoffmann, the physician who first brought the fossils to wider attention. The largest known species of Mosasaurus is called Mosasaurus hoffmanni. Scientists estimate that it could grow up to 12 metres long. That's almost 40 feet. With such an enormous body, Mosasaurus was one of the biggest mosasaurs ever to swim in the oceans. Its skull was strong and heavy, with large, sharp teeth made for slicing through prey. Its jaw muscles were powerful enough to deliver crushing bites. Mosasaurus had 4 limbs, but they weren't legs. Instead, they had evolved into broad, paddle-like flippers that helped it glide and steer through the water. Its long tail ended in a downward curve with a fluke, similar to the tail fin of a modern-day shark, which it used to propel itself forward. Interestingly, while Mosasaurus had excellent eyesight for spotting prey in the open sea, its sense of smell was not very good. It may have been warm-blooded, something quite rare among reptiles, because it had a high metabolism. This trait, which is called endothermy, allowed it to stay active in cooler waters. Not all species of Mosasaurus looked the same. Some were heavily built, like Monsieur Hoffmanni, while others were slimmer and more snake-like, such as Monsieur Lemonnieri. However, for many years, scientists were confused about how to tell the species apart because the original fossil descriptions weren't clear. Over 50 different species were once placed in the Mosasaurus group. Fortunately, a careful restudy of the original fossils in the year 2017 helped clear up the confusion and confirm that at least 5 species rightfully belong to the genus Mosasaurus. Another 5 are still being studied and may be reassigned. Fossils of Mosasaurus have been found across the globe, showing that it lived in many different parts of the ancient oceans. These remains have been discovered in places like North America, South America, Europe, Africa, western parts of Asia, and even Antarctica. Mosasaurus thrived in all kinds of marine climates, from warm tropical waters to chilly subpolar seas. As a giant predator, Mosasaurus sat at the very top of the food chain. It likely hunted a wide variety of sea creatures, including bony fish, sharks, squid-like animals called cephalopods, seabirds, turtles, and even other marine reptiles, including other mosasaurs. Scientists believe that Mosasaurus preferred to hunt in open waters near the surface. Its presence in ancient ecosystems was so significant that it may have changed the balance of life in the seas. For instance, when Mosasaurus appeared in the western interior seaway of North America, many local marine animals disappeared and were replaced by new species, likely due to the pressure Mosasaurus placed on the food web. Still, Mosasaurus did not have the oceans to itself. Other large predatory mosasaurs, such as Tylosaurus and Prognathodon, also roamed the seas and ate similar prey. These marine reptiles probably coexisted by dividing their hunting grounds or specializing in different food sources, a behavior known as niche partitioning. However, they weren't always peaceful neighbors. There is fossil evidence showing that Tylosaurus once attacked a Mosasaurus, and even some Mosasaurus individuals were found with bite marks from their own kind, suggesting fights among rivals. These battles may have involved snout-to-snout grappling, much like what modern crocodiles do. The very first Mosasaurus fossil known to science was uncovered in the year 1764 in a chalk quarry near Maastricht. It was a skull, and at first people thought it might be from a whale. This fossil, now labelled TM7424, is currently on display at the Taylor's Museum in Haarlem, the Netherlands. Around the year 1780, the quarry revealed a second, even more impressive skull. A Dutch physician named Johann Leonard Hoffmann examined it and thought it belonged to a crocodile. He contacted the respected scientist Petrus Camper, who published a study suggesting the fossil came from a whale. The strange bones sparked excitement and curiosity across Europe. In the year 1794, during the French Revolutionary Wars, French troops captured the city of Maastricht, and with it, the now famous fossil. According to a dramatic, and likely exaggerated tale, told by the geologist Barthélemy Faujas de Saint-Fond, in the year 1799, the fossil was handed over in exchange for 600 bottles of wine. Whether or not that story is true, the skull was taken to France and became part of the collection at the National Museum of Natural History in Paris by the year 1795. Later, the son of Petrus Camper, Adrien Gilles Camper, examined the skull and suggested that it belonged to a strange marine lizard, unlike any living creature. Georges Cuvier agreed and published a more detailed study in the year 1808. This research was crucial in changing how scientists thought about extinction and life's history on Earth. Back then, most people believed that fossils were just ancient versions of animals still living today. But Cuvier argued that this was an entirely different creature, and that it had vanished from the planet long ago. In a statement made in the year 1812, Cuvier called the fossil the most important example for understanding the laws of life and the history of the Earth. Then, in the year 1822, William Daniel Conybeare officially named the animal Mosasaurus, using the Latin word for the Meuse River, Mosa, and the Greek word for lizard, sauros. Finally, in the year 1829, Gideon Mantell added the species name Hoffmanni, paying tribute to Hoffmann, the man who had helped bring the great animal of Maastricht to the world's attention. Mosasaurus was one of the most advanced and specialized members of its ancient reptile family, the mosasaurs. These sea-dwelling predators appeared later in the evolutionary timeline and had fully adapted to life in the ocean. Their bodies were shaped like powerful torpedoes for fast swimming, with long tails that bent downward at the tip and ended in a double-lobed fin. They also had two pairs of strong flippers, one in the front and one in the back, to help them glide effortlessly through the ancient seas. In older reconstructions, people once imagined Mosasaurus and its relatives as huge sea serpents with flippers. But scientists now know that these creatures looked more like other big ocean animals that evolved separately but developed similar shapes. This phenomenon is called convergent evolution, and it means Mosasaurus ended up resembling animals like the dolphin-shaped Ichthyosaurs, ancient marine crocodiles, and even early whales. The best-known species of Mosasaurus is Mosasaurus hoffmanni, and it ranks among the largest marine reptiles that have ever lived. However, scientists haven't yet found a complete skeleton of this animal. Most of what we know comes from fossilized skulls. In the year 1967, a paleontologist named Russell noticed that the lower jaw of M. hoffmanni seemed to be about 1/10 the length of its whole body. Using this ratio, another researcher, Grigoriev, in the year 2014, looked at the largest known jaw from this species, nicknamed the Penza specimen, which measured 171 centimeters long. From that, he estimated the full animal might have been up to 17.1 meters, but other estimates vary. A smaller jaw fragment, which was originally about 90 centimeters but thought to be 160 centimeters when complete, led Lingham Solier to suggest a slightly larger size of 17.6 meters. Some scientists later questioned Russell's 1/10 jaw-to-body ratio, suggesting it might have been too generous. In 2014, Federico Fanti and his team proposed a more modest ratio, about 7 times the skull's length. Based on this, they estimated that a hoffmanni with a skull longer than 145 centimeters long and weigh close to 10 metric tons. Using the same method, researchers in 2024 estimated that the Penza specimen could have been about 12 meters in length. But even this might not have been the upper limit. Some isolated bones hint at even bigger individuals. For example, a single quadrate bone, a bone from the jaw joint, was 150% larger than average. In 2016, scientists led by Everhart suggested that, if scaled up properly, the individual could have been 18 meters long. Whether they used Russell's old ratio or not is unclear, though a study in 2024 thinks they probably did. While Ms. Hoffmanni was a true giant, some of its cousins were smaller but better preserved. Take Mosasaurus lemonnieri for instance. Belgian fossils studied by Louis Dollo suggest it reached lengths of about 7 to 10 meters. One of its skeletons, labelled IRANB 3119, showed that the skull made up about 1/11 of the total body length. Mosasaurus missouriensis was also smaller, with studies in 2014 suggesting it grew to about 8 to 9 metres. In 2016, researcher Street pointed out that the larger individuals of this species had skulls longer than 1 metre. One nearly complete skeleton of M. missouriensis measures around 6.5 metres in total, with a skull close to 1 metre in length. Another species, Mosasaurus bogae, is known from fossils found in Morocco. Based on these remains, scientist Nathalie Bardet and her team in 2015 believed it reached lengths of 8 to 10 metres and usually had skulls about 1 metre long. Meanwhile, Mosasaurus conodon, a smaller member of the group, had a skull measuring roughly 98 centimetres. The skull of Mosasaurus was long, strong and cone-shaped, narrowing into a short snout that just slightly extended beyond the front teeth. In Hoffmanni, the snout was more blunt, while in Millemonnieri it was pointed. Along the jaws, small holes called foramina formed neat rows. These holes helped carry nerves to the front of the face, similar to those seen in another mosasaur named Cladoselache. Most Mosasaurus species had thick and deep upper jaws, except for Monsieur Conodon, which had thinner ones. The lower jaws, known as the dentaries, were long and straight in all species. In Monsieur Hoffmanni, the top edge of the lower jaw curved slightly upward. This was also seen in the biggest Millemonnieri skulls, though smaller ones had straighter jaws. A narrow bony ridge called the premaxillary bar ran along the top front of the skull. It was slim and pinched in the middle in species like Mir Hoffmanni and Millemonnieri, but was much thicker and sturdier in Monsieur missouriensis. The nostrils, located high on the skull, were set farther back than in most mosasaurs. Only the genus Gronyosaurus had them farther. These nostrils started above the 4th or 5th tooth of the upper jaw. Inside the skull, the brain cavity, called the neurocranium, was small and narrow compared to other mosasaurs. For instance, the brain of Pleopletocarpus marshi was twice as large despite its smaller body. Even the parts of the brain like the cerebral hemispheres and the occipital lobe had limited space, showing they were relatively small. Interestingly, Mosasaurus also had the smallest parietal foramen, a skull opening linked to a primitive light-sensitive third eye among its relatives. The quadrate bone, which helped connect the lower jaw to the skull, was tall and shaped like a rectangle. It held the parts responsible for hearing, including a drum-like structure in a rounded pit called the tympanic ala. The trachea, or windpipe, likely extended beneath the back of the lower jaw and split into 2 smaller tubes, bronchi, that ran side by side to the lungs. Mosasaurus had large, powerful teeth meant for cutting and grabbing prey. All species had teeth with sharp edges and prism-shaped enamel surfaces, like having multiple flat faces that gave the tooth strength and cutting ability. Most species had 2 cutting edges on opposite sides of each tooth. Some, like Hoffmanni and Monsieur missouriensis, had fine serrations along those edges. Others, such as Monsieur Conodon and Millemonnieri, had smooth edges. Monsieur bogae had teeth with tiny wrinkles, called crenulations, along the edges. Mosasaurus had 4 types of teeth, 3 types on the upper jaw, premaxillary, maxillary, and pterygoid teeth. 1 type on the lower jaw, dentary teeth. Each species had slightly different numbers, and sometimes individuals varied too. One unusual fossil from North Dakota even had 16 pterygoid teeth, much more than normal. Mosasaurus had thecodont dentition, meaning their teeth were deeply anchored into their jaws with strong roots. Like sharks, they constantly shed and regrew their teeth. One study looked at the tooth of M. Hoffmanni and found it took 511 days for special cells, called odontoblasts, to form the dentin, and about 233 days for the dentin to fully develop. These conclusions were based on tiny growth lines in the tooth, like tree rings, called von Ebner lines. Mosasaurus swam using the powerful muscles in its long, strong tail. Scientists believe its swimming style was what we now call subcarangiform, a method seen today in sleek, fast fish-like mackerels. This style involves the body gently waving from side to side, with most of the movement concentrated near the tail. Its limbs had evolved into large paddle-shaped flippers that worked much like hydrofoils, tools that helped the creature steer through the water with skill and precision. These flippers weren't just simple limbs. They had a special setup. Big muscles attached from the outside edge of the upper arm bone, called the humerus, to the two lower arm bones, the radius and ulna, allowing the flippers to rotate more freely. This gave Mosasaurus better control while swimming and turning. However, using these flippers so powerfully may have come at a cost. One fossil from a Mosasaurus hoffmanni shows damage to the hip bone, the ilium, where the top part of the bone was pulled away from the rest, probably caused by the repeated strain and twisting forces during swimming. When scientists studied the microscopic structure of Mosasaurus bones, they found clues that this sea reptile had a very high metabolism, higher than any modern-day squamate, the group of reptiles that includes lizards and snakes. Its resting metabolic rate, the energy it used while doing nothing, was somewhere between that of today's leatherback sea turtle and ancient marine reptiles like ichthyosaurs and plesiosaurs. This evidence suggests that Mosasaurus was endothermic, meaning it could generate and maintain its own body heat regardless of the water temperature. That would have been a huge advantage, especially in colder regions. While there's no direct evidence proving that Mosasaurus itself was warm-blooded, studies on its close relatives such as Cladoselache strongly support the idea that all mosasaurs might have had this ability. If true, it would be extremely rare among squamates. Only the Argentine black and white tegu, a modern lizard, is known to show a similar ability today. Being warm-blooded gave Mosasaurus an edge. It could swim for longer, chase prey more easily, and explore larger hunting areas. It might even explain how it was able to live in colder parts of the world, including ancient Antarctica. Mosasaurus had large eye sockets, and inside them were thick, bony rings called sclerotic rings. These rings are often linked with the large eyes, and large eyes usually mean good vision. However, the eye sockets were located on the sides of the skull. This meant Mosasaurus didn't have very good depth perception. Its field of binocular vision, the overlap from both eyes, was only about 28.5 degrees, but what it did have was an excellent ability to see across wide, flat areas, perfect for spotting things in the near-surface waters where it likely spent most of its time. Fossil brain casts, essentially moulds of where the brain once sat, have given us clues about Mosasaurus's senses. The parts of the brain responsible for smell, especially the olfactory bulb and vomeronasal organ, were small and underdeveloped in Mosasaurus hoffmanni. This suggests that this species had a poor sense of smell. Another species, Mosasaurus lemonieri, had slightly better developed smell organs, but they were still quite small. All of this tells us that Mosasaurus probably didn't rely much on smell to hunt or find food. Instead, it most likely depended on its sharp vision, and perhaps its hearing or ability to sense vibrations in the water. Most paleontologists agree that Mosasaurus was an active and aggressive predator. It likely hunted a wide variety of sea creatures, including bony fish, sharks, squid-like animals, called cephalopods, birds, turtles, and even other mosasaurs. It probably wasn't a scavenger, since it didn't have a strong sense of smell, something scavengers usually rely on to find dead animals. With its massive size and strong, sharp teeth built for cutting, Mosasaurus was one of the most powerful predators in the ancient oceans. Some scientists have described its hunting style as savage. For example, fossils of the giant sea turtle Evolutionary hoffmanni have been found with huge bite marks, and healed injuries to Mosasaurus jaws show that it sometimes got into fierce fights, either with prey or rivals. Mosasaurus likely preferred to hunt near the ocean's surface, using its large side-facing eyes to scan the water around it. But there's also evidence that some species, like Mosasaurus lemonieri and Mosasaurus conodon, could dive and hunt in deeper water too. A special kind of chemical study on the bones of Mosasaurus hoffmanni revealed extremely low levels of a carbon isotope called D13C. Among all mosasaurs tested, the largest M. hoffmanni individuals had the lowest D13C levels. In ancient ecosystems, animals that feed at the very top of the food chain tend to show these low values, especially if they eat fatty prey like sea turtles or other large reptiles. This means Hoffmanni was not just any predator, it was an apex predator, the ruler of its domain. Further studies of toothwear in Hoffmanni show that it wasn't picky about its meals. It had a generalist diet, meaning it ate a wide variety of animals, This also seems true for another species, Mosasaurus missouriensis. So far, only 2 Mosasaurus fossils have been found with preserved remains of their last meals. The first is from a small Mosasaurus missouriensis skeleton, about 75 million years old. Inside its body, scientists found the remains of a fish that was about 1 metre long, much longer than the mosasaur's own skull, which was only about 66 centimetres long. The fish had been torn apart and eaten in pieces, showing that M. missouriensis could handle prey larger than its head. This species probably focused on prey best suited to its slicing teeth, while other nearby mosasaurs, like Prognathodon, went after tougher prey like shelled animals. This is a good example of how different predators can share an ecosystem by focusing on different types of food. The second fossil comes from a younger Mosasaurus hoffmanni, discovered near the same spot in the Netherlands where the first fossil of this species, the holotype, was found. Nicknamed Lars, this specimen contained the acid-damaged bones of a baby turtle, likely a Anomalocaris, along with bones from other unknown animals. There were even bird-like bones nearby which might have also been part of the mosasaur's last meal. One of the most fascinating discoveries involves a fossilised nautiloid, a squid-like creature with a shell called Argonautilus catarinae. This fossil had bite marks made by 2 mosasaurs. One bite was from a juvenile and the other was from an adult. Both bites were on the part of the nautiloid where its head would have been, suggesting it was already dying or dead when attacked. A 2004 study proposed a striking idea. The adult mosasaur may have been teaching its young how to hunt. Although it's possible the 2 bites came from the same mosasaur biting twice, the differences in tooth spacing show that the jaws came from different-sized animals. This adds to the idea that mosasaurs may have had more complex social behaviour than we once thought. Placoderms were a fascinating group of ancient fish, now extinct, that once ruled the oceans, lakes and rivers hundreds of millions of years ago. Their name comes from 2 ancient Greek words, plax, meaning plate, and derma, meaning skin. A fitting description, since these fish were protected by tough armour-like plates that covered their heads and the front parts of their bodies. These armoured fish belong to a group called Placodermi, a class of early vertebrate animals. Although most of their skeletons were made of cartilage, much like modern-day sharks, the front half of their bodies was shielded in interlocking bony plates, while the rest of their bodies could be covered in scales or left bare, depending on the species. Placoderms first appeared in the ancient seas during a time known as the Silurian period, which began around 443 million years ago. They thrived especially during the Devonian period, which began around 419 million years ago and ended around 359 million years ago, a time often called the Age of Fishes because of the incredible variety of aquatic life. One of the most important reasons placoderms are famous is that they were among the very first fish to have jaws. Scientists believe these jaws developed from the front set of gill arches, structures that originally helped fish breathe. Placoderms also seem to be the earliest vertebrates to have real teeth, made from both bone and dentine, with a soft centre called a pulp cavity. These teeth were likely the ancestors of those seen in modern jawed animals. But placoderms didn't just stop at jaws and teeth, they also developed pelvic fins, the second pair of fins located on the lower part of their bodies. These fins were important evolutionary steps toward the development of hind limbs in land animals, like legs in humans and other tetrapods. Some of the most astonishing discoveries about placoderms came from the Gogo Formation, a fossil-rich site in Western Australia. There, paleontologists uncovered fossils of 3 genera, Metapiscis, Incissoscutum, and Ostrotictodus, that were over 380 million years old. These fossils showed that placoderms were the first known vertebrates to give birth to live young rather than laying eggs. One remarkable fossil, only about 25 centimetres long, contained a 6 centimetre long baby still attached by an umbilical cord. This small fish, named Metapiscis attenboroughi, in honour of David Attenborough, pushed the origin of live birth invertebrates back by more than 200 million years. Placoderm males use specialised organs called claspers to fertilise females internally. Unlike modern sharks, whose claspers are modified parts of their pelvic fins, the placoderm claspers likely developed independently from different parts of the body. They were more flexible and could even be rotated forward, making reproduction easier. Scientists now understand this as a case of convergent evolution, where similar structures evolve in unrelated species due to similar needs, like mating in water, but from different origins and genetic pathways. These fish came in many shapes and sizes. Some, like the Antiarchs, lived at the bottom of rivers and shallow seas and used their jointed, armoured pectoral fins to crawl along the floor. One genus of Antiarch, Bothriolapis, was especially common during the Middle to Late Devonian, with more than 100 known species. Others, such as Arthrodires, were active predators that swam freely through the water column, often far above the seabed. Perhaps the most terrifying of all was Dunkleosteus torelli, one of the largest known Arthrodires. This monstrous fish could grow to lengths between 3.5 to just over 4 meters, or between 11 and 13 feet. It had enormous armoured jaws and is believed to have been a top predator, possibly the very first superpredator among vertebrates, feeding on other large fish and even fellow predators. Its fossils have been found across Europe, North America, and possibly even in Morocco, suggesting it had a wide range. Other placoderms, such as Physiology and Rolfosteus from Australia, were built for speed. They had bullet-shaped head armour that made them streamlined for fast swimming. Another example, Amazicthus, had body shapes similar to today's open water swimmers, hinting that many Arthrodires were agile hunters who actively chased their prey rather than waiting in ambush. Not all placoderms were carnivores, though. Some species, like Holonema, fed on plants, while others, like the enormous Titanichthys, along with members of the families Homostidae and Heterosteus, likely filtered plankton from the water, much like today's whale sharks or basking sharks. Although placoderms dominated the ancient seas for tens of millions of years, their reign came to an end during a massive extinction event known as the Hangenberg event, which occurred around 359 million years ago. This event wiped out all placoderms, leaving the world's waters open for new groups of fish, like the bony fishes, Osteichthyons, and cartilaginous fishes, Chondrichthyons, to rise and take over. Some studies suggest placoderms were not a single unified group, but rather several distinct lineages that all branched off close to the ancestors of today's jawed vertebrates. However, a research study from the year 2016 proposed that placoderms might, in fact, form a single group that shares a common ancestor. Even today, placoderms continue to teach scientists new things about evolution. For example, a study on a placoderm called Colomaspis showed that parts of the vertebrate shoulder, like the bones in our own shoulders, may have evolved from ancient gill structures. The first serious scientific studies on placoderms, a strange group of ancient armoured fish, were carried out nearly 2 centuries ago. Between the years 1833 and 1843, a Swiss naturalist named Louis Agassiz published a massive 5-volume work on fossil fish. At that time, the true nature of placoderms was still a mystery. Scientists back then believed they were jawless creatures, similar to another group of ancient armoured fish known as ostracoderms. In fact, some naturalists went even further and suggested that placoderms might not even be fish at all. They could be shelled invertebrates, or perhaps even turtle-like animals with hard protective coverings. But things began to change in the late 1920s, thanks to the meticulous work of Dr. Erik Stensier, a paleontologist at the Swedish Museum of Natural History in Stockholm. Dr. Stensier was determined to uncover the real structure of these long-extinct creatures. He used fossil specimens that had remarkably well-preserved skulls, and he studied them in a way that was both brilliant and destructive. With great care, he ground away the fossils layer by layer, removing just 1/10 of a millimetre at a time. After each thin layer was removed, he pressed the fresh surface into wax to create an imprint. Eventually, the original fossils were entirely worn away, sacrificed in the name of science. But Dr. Stensier used the wax impressions to build large, 3-dimensional models of the skulls. These models allowed him to study the tiny details of placoderm anatomy like never before. Dr. Stensier concluded that placoderms were not jawless or turtle-like at all. Instead, he believed they were true-jawed fish, early relatives of sharks. At first, many of his fellow scientists were skeptical. Some thought that he was trying too hard to connect placoderms with sharks and forcing the evidence to fit his theory. But over time, as more and more fossils were uncovered and studied, it became clear that Stensia was mostly right. Placoderms were eventually accepted as a sister group to sharks and other cartilaginous fish, also known as chondrichthyans. Many years later, stunning new fossil discoveries were made at a site called Gogo Reef, in what is now Western Australia. The fossils from Gogo were incredibly well preserved, so fine in detail that even soft tissues and delicate bones could be studied. These fossils revealed that placoderms were more than just relatives of sharks. They actually shared important anatomical traits with several other groups of jawed vertebrates, also known as gnathostoms. For instance, the Gogo placoderms had separate bones around their nasal capsules, just like other gnathostoms. In contrast, modern sharks and bony fish have those bones fused into the brain case. Even more surprising, placoderms also shared unique features with osteostracans, a group of jawless fish. These shared traits suggested a deeper evolutionary connection. Because of all this new evidence, scientists eventually revised their thinking again. The older idea, that placoderms were most closely related to sharks, was replaced. Now, most experts believe that placoderms belong to the very base of the gnathostom family tree. In other words, they are no longer seen simply as relatives of sharks, but as some of the earliest jawed vertebrates ever to exist, distant ancestors of all modern fish and even land animals, including us. Trilobites were strange and fascinating animals that once lived in the oceans long before the age of dinosaurs. They belonged to a group of animals called arthropods, the same group that includes crabs, insects and spiders today. But trilobites are now extinct. They make up their own class of ancient arthropods called Trilobita. They first appeared around 521 million years ago, during the early part of the Cambrian period, and they finally disappeared about 251 million years ago, during the Great Mass Extinction at the end of the Permian period. Over this vast span of time, more than 22,000 different species of trilobites lived and thrived in ancient seas across the planet. One reason we know so much about trilobites is that their bodies had hard outer shells made of a mineral called calcite, which fossilizes very well. Because of this, trilobites left behind a huge number of fossils that scientists have studied for centuries. These fossils have helped researchers understand how ancient life evolved, how the Earth's continents moved, and how different layers of rock can be dated using tiny fossils, an important part of a science called biostratigraphy. Trilobites belong to a group of animals called Arthropoda, which includes other soft-bodied creatures that looked like trilobites, but didn't have the same hard shells. Scientists are still trying to figure out exactly how trilobites and other arthropods are related to each other. Trilobites came in many shapes and sizes and lived in many different ways. Some crawled along the seafloor looking for food, either as predators, scavengers, or creatures that filtered tiny particles from the water. Others swam through the water, catching plankton. Some researchers even think a few types may have briefly crawled onto land. Their lifestyles were as varied as those of modern marine arthropods, like crabs and shrimp, except for one thing. There is little evidence that any trilobites were parasites. However, this is still debated among scientists. One special group of trilobites called Olenidae is believed to have formed partnerships with bacteria that ate sulfur. These bacteria may have lived inside or near the trilobites, providing them with food. Trilobites came in many sizes. The biggest ones could grow longer than 70 centimeters, that's more than 2 feet, and may have weighed as much as 4.5 kilograms, or nearly 10 pounds. Trilobites appeared suddenly in the fossil record during a time known as the Cambrian explosion, a period when life on Earth rapidly became more complex. They spread quickly across the globe and became one of the most successful and diverse groups of animals during the Cambrian and the following Ordovician period. They continued to thrive in the Silurian and early Devonian periods, but then their numbers began to fall. Several extinction events such as the Taganic event, the Kellwasser event, and the Hangenberg crisis wiped out many trilobite species. By the time the Carboniferous period began, only one group called Proetida had survived. These final trilobites managed to hold on for millions of years, but their diversity never recovered. Eventually, during the Great Mass Extinction at the end of the Permian period, about 251.9 million years ago, even the last remaining trilobites vanished forever. Trilobites had some of the most complex eyes ever seen in early animals. Some species had huge eyes made up of many tiny lenses, thousands in some cases. These eyes were compound, similar to those of modern insects and crustaceans. The lenses were arranged in neat hexagonal patterns and were made of transparent calcite. This is unusual because most animals have soft lenses, but trilobites used crystals. Some trilobites, like Phacops rana and Ebenochelea beni, had large, prominent eyes for spotting predators or prey in well-lit waters. Others, especially those that lived deep in the ocean where light could not reach, were completely blind. These blind species lost their eyesight over time because they no longer needed it. The structure of trilobite eyes was so advanced that it matched optical principles discovered much later by famous scientists like René Descartes and Christian Huygens in the 17th century. In some trilobites, the eye lenses were shaped in a way that gave excellent focus and depth, just like a modern camera lens. In certain species, like Olenoides serratus, fossil evidence shows extra antenna-like structures sticking out from the back of the body, possibly used for sensing the environment. Most trilobites had a pair of flexible antennae near the head that could be tucked in when the trilobite curled up for protection. The fossil record of trilobites is incredibly complete, especially when it comes to their eyes. This allows scientists to track how trilobite vision changed over time. Although soft tissues usually don't fossilize, the eyes of trilobites were hard enough to survive for hundreds of millions of years. Some trilobite eyes even had sublensa structures, tiny sensory parts beneath each lens, very similar to what we see in the eyes of modern arthropods like horseshoe crabs. These discoveries help scientists understand not only the biology of trilobites, but also how eyesight itself may have evolved long before the Cambrian period. Among the different kinds of eyes that trilobites had, holocrol eyes were the oldest and by far the most common. These eyes were made up of a huge number of tiny lenses, sometimes more than 15,000 in a single eye. Each lens was incredibly small, usually between 30 and 100 micrometers wide, which is much smaller than the width of a human hair. All these lenses were packed tightly together in a neat hexagonal pattern, kind of like the tiles in a beehive. They all touched each other directly, and together they were covered by a single transparent layer called a corneal membrane, which acted like a big shared window. Holocrol eyes were the standard type of eye for almost all trilobites, and they were present from the beginning to the very end of the trilobite's long history on Earth. They were found in every major group of trilobites except for one, the Agnostida. However, scientists still don't know much about how these eyes evolved in the earliest trilobites, because fossils from the lower and middle Cambrian periods, more than 500 million years ago, often do not preserve the surface of the eye very well. The performance of these eyes depended on several things: how much light there was in the environment, how the trilobite moved in circles to scan its surroundings, how densely the eye lenses were packed, the angle at which light hit the eye, and how the signals from each light-sensitive cell, called a rhabdom, were processed by the trilobite's nervous system. For example, in dark environments, trilobites like Pracyclopyge needed bigger lenses to capture more light. In contrast, faster-moving trilobites like Carolinites had flatter eyes on the sides and more curved areas in the front and back, helping them see better in the direction they were swimming. In this way, the shape and structure of a trilobite's eyes can give scientists clues about how it lived, what kind of environment it lived in, and whether it was a hunter, a prey animal, or something else. Another type of eye seen in trilobites is called the schizocroal eye. These were quite different from the holocrol ones. Instead of having thousands of tiny lenses, schizocroal eyes had fewer, usually around 700, but much larger lenses. Each of these lenses had its own cornea, its own transparent covering, and unlike holocrol lenses, they didn't touch each other. Instead, they were separated by thick layers of cuticle, known as sclera. These eyes only appear in one group of trilobites called Phacopina, and they seem to have suddenly evolved in the early part of the Ordovician period, which was more than 480 million years ago. Most scientists believe schizocroal eyes developed from earlier holocrol eyes. The placement and design of these eyes suggest that they weren't used for hunting, but rather for spotting danger. Trilobites with schizocroal eyes may have used them like an early warning system, helping them detect predators before they needed to roll up their bodies defensively. For a long time, no modern animals were thought to have similar eyes. However, researchers eventually found that an insect called Xenos pecci has eyes that work in a similar way, showing that nature can come up with similar solutions across time. A third and much rarer kind of eye, called the abathocrole eye, was only found in a special group of early trilobites known as Eodicina, which lived during the Cambrian period more than 500 million years ago. These eyes had about 70 small lenses, and each lens had its own cornea. The lenses were separated by a thinner sclera than what was seen in schizocrole eyes. Although fossils of these eyes are rare and not always well preserved, scientists have confirmed that abathocrole eyes are among the earliest types of eyes ever found in the history of life on Earth. Interestingly, many of these trilobites later lost their eyes entirely, probably because of changes in their environment. This shows how animals can lose complex organs like eyes if they are no longer needed. Losing eyesight was not rare in trilobites. In fact, some groups, especially those that lived for many millions of years, frequently became blind. This happened in trilobite families like the Agnostida and Trinucleoidea. In other groups, such as Proetida and Phacopina from western parts of Europe, including the Tropidocoryphonae from France, scientists have found clear fossil evidence showing how eyes slowly became smaller and simpler over time until they disappeared completely. This change probably happened gradually, over many generations in response to new environments, like deep or murky waters, where sight wasn't useful anymore. Besides their main eyes, trilobites might have had other ways of sensing the world. One fascinating example is the macula, a small thin patch of cuticle found on the underside of the trilobite's mouth part, called the hypostum. In some species, scientists believe these maculae may have acted like simple ventral eyes that help the trilobite tell day from night or navigate while swimming upside down. There were also other unusual features on trilobite bodies called prosopon, tiny structures on their outer shell. Some of these may have been sensory tools for detecting chemicals in the water or vibrations, much like how modern animals sense their surroundings. In particular, some trilobites, like those in the Harpetida and Trinucleoidea groups, had wide, pitted fringes on their heads. These trilobites often had tiny eyes or none at all. Because of this, some researchers believe that these fringes might have acted like a kind of compound ear, helping the trilobite detect sounds or vibrations in the water, offering a completely different way of perceiving the world. Ichthyosaurs were a group of giant marine reptiles that ruled the oceans long ago. While the scientific name Ichthyosauria refers to a specific order of these creatures, the word ichthyosaur is often used more broadly to describe all of their relatives. They were not dinosaurs, but they lived during the same age and the mighty Mesozoic era, which stretched from about 250 million to 66 million years ago. These incredible creatures first appeared around 250 million years ago during the early Triassic period. Scientists believe they evolved from land reptiles that went back into the water, just like how, millions of years later, some mammals like whales and dolphins returned to the sea. Over time, these early ichthyosaurs transformed completely into fast-swimming ocean dwellers. This kind of transformation, where unrelated animals end up looking similar because they adapt to the same environment, is called convergent evolution. That's why ichthyosaurs came to look so much like dolphins, even though they were reptiles and not mammals at all. Ichthyosaurs were especially common during the late Triassic and early Jurassic periods, but eventually other sea reptiles called plesiosaurs began to take over as the top predators of the oceans. Even so, ichthyosaurs held on for a long time, and did not truly disappear until around 90 million years ago during the late Cretaceous, likely due to major changes in the climate and environment. Scientists first discovered ichthyosaur fossils in the early years of the 19th century in England. In the year 1834, the group was officially named Ichthyosauria. Later in that century, even more beautifully preserved fossils were uncovered in Germany, some with soft tissue still intact. Since the late 20th century, interest in these ancient sea reptiles has grown again, and now over 50 different genera of ichthyosaurs have been identified on every continent. Ichthyosaurs came in many sizes. Some were as small as 1 foot long, while others were true giants. One species from the Triassic period, Shonosaurus popularis, grew to nearly 50 feet in length. Another, Shonosaurus sicaniensis, may have reached 70 feet. In 2018, jawbones found in England hinted at an Ichthyosaur that could have been between 66 and 82 feet long, the length of a large city bus. These remains were later named Ichthyotitan sevenensis. Most ichthyosaurs looked like a mix between a fish and a dolphin. They had long, slender bodies, short necks, pointed snouts, and powerful tails with a fin that pointed mostly downward. Their limbs had completely transformed into flippers, which sometimes had extra digits and joints to help them steer in the water. Some species even had dorsal fins on their backs. Their eyes were especially huge, not just for their bodies, but among all animals ever known. These massive eyes helped them see in the deep, dark parts of the ocean. A circular ring of small bones called a scleral ring protected their eyes from the crushing pressure of deep-sea diving. Despite being reptiles, ichthyosaurs did not lay eggs. Instead, they gave birth to live young in the water. They were also warm-blooded and likely had a layer of blubber under their skin, much like modern whales and dolphins. This helped them stay warm in cold seas. Their diet varied by species. Many ate fish and squid, catching them with long cone-shaped teeth. Others had broad, flat teeth perfect for crushing shellfish. Some species, like Thalatarchon, were powerful predators with sharp blade-like teeth that could take down large prey. As ichthyosaurs became fully aquatic, their skeletons also changed dramatically. The vertebrae, the bones in their backbone, gradually lost their interlocking parts, becoming more like simple rounded discs. This disc shape made their spines more flexible and better suited for swimming. Their necks were very short, bringing their large heads closer to their bodies, and their tails developed a downward bend that helped power strong, efficient strokes through the water. They had thin ribs and a set of belly ribs called gastralia that were not fused together like a turtle shell. Their shoulder bones and limbs also evolved over time. Early species had limbs that still looked somewhat like those of land reptiles, but later ichthyosaurs had flippers filled with dozens of tiny disc-shaped bones, forming long rows of finger-like elements. Some species had extra fingers, even up to 10 per flipper. This helped make their flippers into powerful hydrofoils for smooth, speedy swimming. The back flippers, or hind limbs, were usually smaller than the front ones and had fewer bones. Even their hips were reduced. The bones were no longer connected or fused as in land animals. In some advanced species, the hip bones did not even touch each other. The ichthyosaur skull was one of its most distinctive features. The snout was long and narrow, packed with sharp teeth, especially in the upper jawbone called the premaxilla. The eye sockets were enormous, taking up most of the side of the head. The top and rear parts of the skull changed shape over time, and in later species many skull bones became so compressed and fused that it was hard to tell them apart. Some species even had a narrow ridge running along the top of their skull, where muscles attached to help snap the jaws shut with force. Interestingly, while most reptiles have a small opening on top of their heads called a parietal eye in ichthyosaurs, this opening gradually moved toward the front of the skull. Their ears were adapted for underwater hearing, and they lacked teeth in the roof of the mouth, unlike some other reptiles. The earliest ichthyosaurs had long eel-like bodies and swam with sinuous snake-like motions, but over millions of years they evolved into sleeker, faster swimmers, more like today's tuna or dolphins. Their flippers became stiffer, and their tails more powerful, allowing for high-speed chases through the sea. Stephen Jay Gould, a famous evolutionary biologist, once called the ichthyosaur his favourite example of convergent evolution. Even though they were reptiles, ichthyosaurs evolved to look just like dolphins, with a similar body shape, flippers and tail, all because they lived in the same kind of environment and needed to solve the same challenges of swimming, hunting and surviving in the ocean. In the year 2024, scientists discovered fossil fragments from what may be the largest ichthyosaur ever found, jawbones longer than 80 feet. If confirmed, this ancient sea dragon would have rivaled the largest animals ever to swim in Earth's oceans, including the mighty blue whale. Fossils that preserve the skin of ichthyosaurs usually suggest that their skin was smooth, stretchy, and did not have any scales. However, most of these fossils are not true impressions of the skin itself. Instead, they show outlines that were formed by bacterial activity around the decaying body. In one rare case, a real impression of Ichthyosaur skin was found in a fossil of a species called Eurypterid, discovered in the Solnhofen Plattencalc rock formations in Germany. These rocks are known for preserving extremely fine details. In this special fossil, very tiny scales seem to be visible. Figuring out what colour ichthyosaurs were is quite tricky. Back in the year 1956, a scientist named Mary Whitehair said she found pigment cells, called melanocytes, in the skin of a British Ichthyosaur fossil known as R509. These cells seem to still contain reddish-brown pigment grains. For a long time, scientists believed that ichthyosaurs had a colour pattern called countershading, dark on top and light underneath, just like modern sharks, penguins, and many other animals that use this pattern to hide while hunting in the water. But in the year 2014, a new discovery challenged this idea. A group led by Johan Lindgren from Lund University found special pigment structures called melanosomes, which contain black melanin, in the skin of an ichthyosaur fossil named Eurypterid 1993.338. Based on this, the researchers concluded that ichthyosaurs were likely dark all over. This dark colouring may have helped them stay warm in cold water and blend into the deep sea when hunting. This was different from the colour patterns seen in other prehistoric sea creatures like mosasaurs and ancient leatherback turtles, which did show clear countershading. However, in the year 2015, another group of scientists questioned Lindgren's conclusions. They pointed out that having a layer of melanosomes in the skin is common in reptiles, but it doesn't always mean the animal was dark-coloured. Reptile skin colour is also affected by other types of pigment cells, such as iridophores, which reflect light, xanthophores, which make yellow, and erythrophores, which make red. These other types of cells are rarely preserved in fossils, so we don't really know if Eurypterid 1993.338 was actually dark, countershaded, green, or even had a more complex pattern. Later, in the year 2018, Lindgren and his team updated their view. They suggested that ichthyosaurs may indeed have had countershading, based on how pigment cells were distributed in another ichthyosaur species called Stenopterygius. As for their digestion, scientists have occasionally found gastroliths, small stones that some animals swallow, inside ichthyosaur fossils. These stones might have helped break down food or help the animal stay balanced in the water. Gastroliths have been found in only a few cases, such as in fossils of Nanopterygius and Pangiangsaurus. On the other hand, fossilised ichthyosaur poop, called coproliths, is actually quite common. In fact, the famous fossil hunter Mary Anning was already collecting and selling these fossilised droppings back in the early 19th century.